Welcome back to the quiet between the stars. I hope you have found a comfortable place to rest. Tonight, we embark on a journey that spans scales almost beyond human comprehension. We will travel from our home inside the Milky Way, a spiral galaxy containing somewhere between 200 and 400 billion stars, outward through the cosmic web, past galaxy clusters and superclusters, until we reach the emptiest places in the known universe. These are the cosmic voids, regions stretching hundreds of millions of light years across, where the density of matter drops to nearly nothing. In the Bootes void alone, a sphere roughly 330 million light-years in diameter, astronomers have found only 60 galaxies, where thousands should exist. We will begin here, orbiting our own sun, and gradually pull back through the Orion Spur, past the galactic core where a supermassive black hole called Sagittarius A star holds 4 million solar masses in its grip. From there, we drift beyond the Milky Way entirely, through the local group, past Andromeda, and into the vast filaments and empty spaces that define the largest structures in existence. If these quiet explorations help you find rest at the end of your day, please consider liking this video and subscribing to the channel. Your support allows us to continue these journeys together. Now, let your breathing slow. Let the weight of the day settle. The stars are waiting, and we have a very long way to travel. Before the first heartbeat of time, before light or darkness had meaning, there exists a boundary so fundamental that physics itself cannot see beyond it. This is the Planck epoch, a sliver of existence lasting just 10 to the negative 43 seconds, a decimal point, followed by 42 zeros before reaching the number 1. In this inconceivably brief moment, the entire observable universe, everything that will become hundreds of billions of galaxies, occupies a space smaller than 10 to the negative 35th meters, a length known as the Planck length. To grasp this scale, consider that a single proton is roughly 10 to the 20 times larger than this primordial seed of reality. At this instant, the universe possesses a temperature of approximately 10 to the 32nd Kelvin, a number so extreme that it defies intuition. The core of our sun burns at a mere 15 million Kelvin. The hottest moments of thermonuclear explosions reach perhaps 350 million Kelvin. Yet the Planck temperature exceeds these by factors of trillions upon trillions. At such energies, each particle carries roughly 10 to the 19th billion electron volts, the Planck energy, enough that quantum gravitational effects become as significant as the other fundamental forces. Here, the 4 forces we know today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, do not exist as separate entities. They are unified into a single superforce, a primordial interaction whose mathematical description remains one of the great unsolved problems of physics. General relativity, Einstein's elegant theory of gravity as curved space-time, breaks down at these scales. Quantum mechanics, the framework governing the subatomic world, similarly loses its footing. The 2 pillars of modern physics, so successful in their separate domains, cannot be reconciled in this extreme regime. The very concept of space-time becomes uncertain. At the Planck scale, quantum fluctuations are so violent that the smooth fabric of space and time dissolves into what physicists sometimes call quantum foam. Imagine the surface of an ocean viewed from an airplane. it appears flat and calm. But descend to the scale of individual water molecules, and that smoothness vanishes into chaotic thermal motion. Similarly, space-time at 10 to the negative 35th meters is not the continuous stage upon which physics plays out, but rather a seething, probabilistic froth where geometry itself fluctuates wildly. In this epoch, the distinction between space and time may not even be meaningful. The arrow of time, that familiar sense of past flowing into future, requires a thermodynamic framework that does not yet exist. Entropy, the measure of disorder that gives time its direction, has no clear definition when the universe is a single quantum state of maximum energy density. Some theoretical frameworks suggest that time itself emerges from more fundamental quantum gravitational degrees of freedom, crystallizing out of the Planck epoch, like ice forming from supercooled water. The energy density during this moment reaches approximately 10 to the power of 97 kilograms per cubic meter. For comparison, the density of an atomic nucleus, the densest stable matter known, is roughly 10 to the power of 17 kilograms per cubic meter. The Planck density exceeds this by 80 orders of magnitude. If you could somehow compress the entire mass of the observable universe into a single proton, you would still fall short of this primordial concentration by a vast margin. What physical laws govern this regime? String theory offers one possibility, suggesting that at these scales, the fundamental constituents of reality are not point particles, but tiny vibrating strings of energy, roughly 1 Planck length in size. Different vibrational modes of these strings would correspond to different particles: electrons, quarks, photons, gravitons. In this picture, the apparent diversity of matter and forces emerges from a single underlying entity, much as different musical notes emerge from the same violin string. Loop quantum gravity proposes an alternative vision, where space-time itself is quantized into discrete chunks. Rather than a continuous fabric, space would be woven from finite loops of gravitational field, with areas and volumes coming in minimum units related to the Planck length. In this framework, the Big Bang singularity, the point of infinite density predicted by classical general relativity, might be replaced by a big bounce, where a previous contracting universe reached maximum density and rebounded into expansion. Neither theory has been confirmed by experiment. The energies required to probe Planck scale physics directly exceed the capabilities of any conceivable particle accelerator by roughly 15 orders of magnitude. The Large Hadron Collider, humanity's most powerful machine, reaches energies of about 10 to the 13th electron volts. The Planck energy is 10 to the 28th electron volts. To bridge this gap would require an accelerator larger than our solar system. Yet the Planck epoch is not merely theoretical speculation. Its consequences ripple forward through cosmic history. The quantum fluctuations born in this moment, amplified by the inflationary expansion that follows, will eventually become the seeds of all cosmic structure. The slight variations in density that these fluctuations produce will, over billions of years, grow into galaxies, clusters, and the vast cosmic web. Every star, every planet, every atom in your body traces its lineage back to perturbations that originated in this first fraction of a second. The universe at 10 to the minus 43 seconds is not empty space containing energy. It is energy so concentrated that the distinction between matter, radiation, and space-time geometry becomes meaningless. The stress-energy tensor, the mathematical object that describes how matter and energy curve space-time in Einstein's equations, dominates so completely that space-time cannot be treated as a fixed background. Everything is dynamic, interconnected, unified. As this epoch ends, as the universe ages past 10 to the minus 43 seconds and cools below 10 to the 32nd Kelvin, gravity begins to separate from the other forces. This is the first symmetry breaking, the first differentiation in a cosmos that will spend the next 100 billion years elaborating complexity from primordial simplicity. The graviton, if it exists as a quantum particle, becomes distinct from the carriers of the other forces. Space-time begins to acquire the smooth, continuous character we recognize today. The transition is not gentle. The energy released as gravity decouples may drive the next phase of cosmic evolution, the exponential expansion known as inflation. But that lies ahead, in the next fraction of a second. For now, in this first Planck moment, the universe exists in a state of maximum mystery, where the deepest questions of physics converge. What is the quantum nature of gravity? Why does the universe exist rather than nothing? Why these laws and not others? These questions have no answers yet. Perhaps they never will. But the universe does not wait for understanding. It simply evolves, cooling and expanding, differentiating and complexifying, carrying forward the quantum information encoded in this first instant toward a future of stars and galaxies, of planets, and perhaps minds capable of wondering about their own origins. The Planck epoch lasts for an unimaginably brief moment, yet it contains the blueprint for everything that follows, written in a language we are only beginning to learn to read. The universe does not hesitate at the edge of comprehensibility. As the Planck epoch ends, at approximately 10 to the minus 43 seconds after the beginning, the cosmos enters a phase that will determine the structure of everything we can observe today. The temperature has already dropped from the Planck temperature of 10 to the power of 32 Kelvin, though it remains inconceivably hot by any familiar standard. Gravity has separated from the other fundamental forces, becoming the first distinct interaction in a universe that will eventually know four. For a brief interval, the strong nuclear force, the weak nuclear force, and electromagnetism remain unified in what physicists call the grand unified force. This era persists until approximately 10 to the minus 36 seconds, when the temperature falls to roughly 10 to the 28th Kelvin. At this threshold, another symmetry breaks. The strong force separates, acquiring its own identity as the interaction that will eventually bind quarks into protons and neutrons. This phase transition releases energy, and this energy triggers something extraordinary. The universe begins to inflate. Inflation is not ordinary expansion. It is exponential growth of space itself, a doubling and redoubling that occurs with astonishing rapidity. In the standard inflationary model, the universe doubles in size approximately every 10 to the minus 37th seconds. This doubling continues for roughly 10 to the negative 32nd seconds, which means the universe undergoes perhaps 60 to 100 doublings in total. To understand what this means, consider that 60 doublings multiplies a quantity by 2 to the 60 power, which equals approximately 10 to the 18th power. 100 doublings produces a factor of 10 to the 30th power. A region smaller than a proton, perhaps 10 to the minus 26th power meters across, expands to become larger than the entire observable universe today. Space stretches faster than light could ever travel through it, and this does not violate relativity because it is space itself that expands, not objects moving through space. The cosmic speed limit applies to motion within space-time, not to the behavior of space-time itself. The energy driving this expansion comes from a hypothetical field called the inflaton field. This field exists in a state of false vacuum, a configuration that appears stable but is not the lowest possible energy state. Like a ball perched on a hilltop, the inflaton field contains potential energy that can be released. During inflation, this potential energy behaves like a cosmological constant, a form of energy density that does not dilute as space expands. Ordinary matter and radiation become less dense as the universe grows, their energy spread across ever larger volumes. But the inflaton field maintains its energy density, and this constant density drives the exponential expansion. The physics of inflation solves several puzzles that had troubled cosmologists for decades. The first is the horizon problem. When we observe the cosmic microwave background radiation, we see light that has traveled for 13.8 billion years from regions that were never in causal contact with each other. Light from one side of the observable universe has not had time to reach the other side, even traveling since the beginning of time. Yet the temperature of this radiation is uniform to 1 part in 100,000 across the entire sky. How can regions that never communicated have the same temperature? Inflation provides the answer. Before inflation, the entire observable universe was contained in a region small enough for light to cross many times. This tiny patch had time to reach thermal equilibrium to smooth out any temperature differences. Then inflation stretched this uniform region to cosmic scales, preserving its homogeneity while expanding it far beyond what light could traverse. The second puzzle is the flatness problem. The geometry of the universe depends on its total energy density. If the density exceeds a critical value of approximately 9.5 times 10 to the negative 27th kilograms per cubic meter, space curves back on itself like the surface of a sphere. If the density falls below this value, space curves the opposite way like a saddle. Only at exactly the critical density is space flat, with the geometry of ordinary Euclidean space. Observations show that the universe is flat to extraordinary precision, within about 0.4% of the critical density. But this flatness is unstable. Any deviation from perfect flatness grows over time. For the universe to be this flat today, it must have been flat to 1 part in 10 to the 60 at the Planck time. This seems like an absurd fine-tuning, a cosmic coincidence demanding explanation. Inflation explains it naturally. Exponential expansion drives any curved space toward flatness, just as inflating a balloon makes its surface appear flatter and flatter to an ant standing on it. No matter how curved the universe was before inflation, the expansion stretches it flat, erasing any memory of its original geometry. The third puzzle is the monopole problem. Grand unified theories predict that when the strong force separated from the electro-weak force, the phase transition should have created magnetic monopoles, particles carrying isolated north or south magnetic poles. These monopoles would be extremely massive, perhaps 10 to the 16th power times the mass of a proton, and they should be abundant, perhaps one for every 10 to the 10th power protons. Yet no magnetic monopole has ever been detected. Inflation dilutes these monopoles to undetectable levels. If monopoles formed before or during the early stages of inflation, the exponential expansion spreads them across such vast volumes that we would expect less than one monopole in the entire observable universe. The monopoles still exist, in principle, but they are so rare that we will never encounter one. Yet inflation does more than solve problems. It creates structure. The inflaton field, like all quantum fields, experiences fluctuations. At the smallest scales, the field does not have a perfectly uniform value, but jitters randomly, borrowing energy from the vacuum for brief instants before returning it. Normally, these fluctuations average out, leaving no lasting trace. But during inflation, something remarkable happens. The exponential expansion stretches these quantum fluctuations faster than they can oscillate back to their average value. Microscopic quantum uncertainty becomes frozen into the fabric of space, imprinted as variations in energy density across cosmic scales. These fluctuations are tiny, perhaps 1 part in 100,000. But they are the seeds of all structure in the universe. Regions with slightly higher density will eventually attract more matter through gravity. Regions with slightly lower density will become voids. The pattern of galaxies and clusters and superclusters, the cosmic web that spans billions of light years, traces its origin to quantum fluctuations during the first 10 to the negative 32nd seconds of existence. The statistical properties of these fluctuations carry specific predictions. Inflation produces a nearly scale-invariant spectrum, meaning fluctuations have roughly the same amplitude at all scales. The spectrum is not perfectly flat, but tilted slightly, with a spectral index of approximately 0.965, meaning larger scales have slightly more power than smaller scales. This prediction matches observations of the cosmic microwave background with remarkable precision. Inflation also produces gravitational waves, ripples in space-time itself generated by quantum fluctuations in the gravitational field. These primordial gravitational waves would leave a distinctive signature in the polarization of the cosmic microwave background, a pattern called B-mode polarization. Detecting this signal would provide direct evidence for inflation and probe physics at energies of 10 to the 16th giga-electron volts, far beyond what any particle accelerator could achieve. As inflation proceeds, the inflaton field slowly rolls down its potential energy hill. The rate of expansion gradually decreases. Eventually, the field reaches the bottom of its potential, the true vacuum state. At this moment, inflation ends. The potential energy stored in the inflaton field must go somewhere, and it converts into a flood of particles and radiation. This process is called reheating. During reheating, the inflaton field oscillates around the minimum of its potential, and these oscillations decay into the particles of the standard model. The temperature of the universe, which had dropped to perhaps 10 to the minus 30 Kelvin during the cold emptiness of inflation, suddenly rises to perhaps 10 to the 27 Kelvin or higher, the universe fills with a dense plasma of quarks, antiquarks, gluons, electrons, positrons, neutrinos, and photons. All the matter and radiation that will eventually form stars and galaxies originates in this moment of cosmic reheating. The entire inflationary epoch, from its beginning at 10 to the power of negative 36 seconds to its end at approximately 10 to the power of negative 32 seconds, lasts for only about 10 to the power of negative 32 seconds. In human terms, this is incomprehensibly brief. If you could somehow count off Planck times, each lasting 10 to the minus 43 seconds, you would count to roughly 10 to the 11th, 100 billion, before inflation ended. Yet in this fleeting interval, the universe transforms from a hot, curved, monopole-filled chaos into a flat, uniform, structure-seeded expanse ready to evolve toward complexity. The seeds are planted. The quantum fluctuations that will become galaxies are frozen into space. The geometry is flattened. The exotic relics of earlier phase transitions are diluted beyond detection. And the universe, now filled with the hot plasma of reheating, continues its expansion and cooling, carrying forward the information encoded during inflation toward a future of nucleosynthesis and recombination of stars and planets of the cosmic microwave background that will preserve the memory of these first moments for observers 13.8 billion years hence. The reheating that follows inflation floods the universe with energy, and from this energy, matter condenses like dew, forming on a cold morning. But this is not the matter of everyday experience, not the atoms that will one day compose stars and planets and the bones of living things. At 10 to the minus 12 seconds after the beginning, the universe exists as something far more fundamental, a seething plasma of quarks and gluons, the most basic building blocks of matter in a state so hot and dense that they cannot yet combine into the protons and neutrons that will later define atomic nuclei. The temperature at this moment defies intuition. The cosmos burns at approximately 10 to the 16th Kelvin, 100 million billion degrees, hotter than the core of any star that will ever exist, hotter than the most violent supernova. At such temperatures, the strong nuclear force, which in cooler conditions binds quarks together into composite particles, cannot maintain its grip. Quarks roam freely through space, accompanied by the gluons that mediate the strong force between them. This is the quark-gluon plasma, a state of matter that existed for only a few millionths of a second in the early universe, but that scientists have recreated in particle accelerators like the Large Hadron Collider and the relativistic heavy ion collider, smashing gold or lead nuclei together at nearly the speed of light to briefly conjure conditions not seen since the cosmos was younger than a heartbeat. The physics of this era is governed by quantum chromodynamics, the theory that describes how quarks interact through the exchange of gluons. Unlike electromagnetism, where the force between charged particles weakens with distance, the strong force behaves paradoxically. At extremely short distances, quarks experience what physicists call asymptotic freedom, moving almost independently of one another. But as they try to separate, the force between them grows stronger, like a rubber band stretched to its limit. In the quark-gluon plasma, the temperature is so extreme that this asymptotic freedom dominates, and quarks behave almost as free particles swimming through a dense soup of their own force carriers. The density of this primordial plasma is staggering. Every cubic centimeter contains energy equivalent to approximately 10 to the 34th power joules, packed into a space smaller than a grain of sand. The quarks themselves come in 6 varieties, called flavors: up and down, charm and strange, top and bottom. Though at this temperature, the heavier flavors, top, bottom, charm, and strange, are constantly being created and annihilated in pairs, their existence fleeting as the plasma churns with creative and destructive energy. The up and down quarks, being the lightest, are the most abundant, and they will eventually become the primary constituents of ordinary matter. Alongside the quarks swim the gluons, 8 types distinguished by their color charge, a quantum property unrelated to visible color, but named for convenience. Unlike photons, which carry no electric charge and therefore do not interact with each other, gluons carry color charge and can interact among themselves, creating a tangled web of force exchanges that makes the quark-gluon plasma behave in unexpected ways. Experiments at particle colliders have revealed that this plasma flows almost like a perfect liquid, with the lowest viscosity of any known substance, a property that emerges from the intense interactions between its constituents. The universe at this moment is also filled with other particles. Electrons and their heavier cousins, muons and tau particles, zip through the plasma, along with their corresponding neutrinos. Photons are present too, but they cannot travel far before scattering off the charged quarks and leptons, making the universe opaque, a glowing fog of energy where light is trapped in an endless series of collisions. The W and Z bosons, carriers of the weak nuclear force, are also abundant. Their masses of approximately 80 and 91 billion electron volts, respectively, making them heavy, but still producible at these extreme temperatures. As the universe expands, it cools. This cooling is relentless, governed by the relationship between energy density and the scale factor of space. By 10 to the minus 6 seconds, approximately 1 microsecond after the beginning, the temperature has dropped to roughly 10 to the 13th Kelvin, still unimaginably hot by any terrestrial standard, but cool enough for a phase transition of profound importance. The quarks, which have roamed freely for a millionth of a second, now find themselves unable to escape the grip of the strong force. They begin to combine 3 by 3 into composite particles called baryons, or in pairs of quark and antiquark into mesons. This transition is called confinement, and it marks the end of the quark-gluon plasma era. The up and down quarks, combining in groups of 3, form protons, each containing 2 up quarks and 1 down quark, and neutrons, each containing 1 up quark and 2 down quarks. The mass of a proton is approximately 938 million electron volts. But remarkably, only about 1% of this mass comes from the quarks themselves. The rest emerges from the energy of the gluon field binding them together, a vivid demonstration of Einstein's equivalence of mass and energy. The neutron is slightly heavier, at about 940 million electron volts, a difference of just 1.3 million electron volts that will have enormous consequences for the future chemistry of the universe. The confinement transition is not instantaneous. but occurs over a brief interval as the universe crosses a critical temperature of approximately 2 × 10 to the 12th Kelvin. Lattice quantum chromodynamics calculations, performed on the most powerful supercomputers, suggest this transition is a smooth crossover rather than a sharp phase change. The quarks gradually becoming confined as the plasma cools rather than snapping suddenly into bound states. The universe transforms from a soup of free quarks to a gas of protons, neutrons, and the lighter mesons called pions, which will soon decay into other particles. But the story of matter at this epoch is also a story of antimatter. For every quark in the plasma, there exists an antiquark, identical in mass but opposite in charge. For every electron, a positron. The universe at 10 to the minus 6 seconds contains nearly equal amounts of matter and antimatter, and as particles meet their antiparticles, they annihilate, converting their mass entirely into energy, into photons that join the radiation bath. This annihilation is mutual destruction on a cosmic scale, and if matter and antimatter were perfectly balanced, the universe would eventually contain nothing but radiation, no atoms, no stars, no planets, no observers to wonder at the night sky. Yet the universe today is manifestly made of matter. The asymmetry that saves existence is tiny, approximately 1 extra quark for every billion quark-antiquark pairs, a ratio of about 10 to the -9th power. The origin of this asymmetry remains one of the deepest mysteries in physics, requiring processes that violate certain symmetries, charge conjugation, parity, and possibly baryon number conservation, in ways that the standard model of particle physics cannot fully explain. Theories involving heavy particles decaying asymmetrically in the early universe, or processes during the electroweak phase transition at 10 to the minus 12 seconds, offer possible explanations, but the question remains open. As the annihilation proceeds, the antimatter is consumed, leaving behind the slight excess of matter that will become everything. By the time the universe is a few microseconds old, the antiquarks have found their quark partners and vanished into radiation, and the surviving quarks have confined themselves into protons and neutrons. The ratio of photons to baryons, set during this annihilation epoch, is approximately 1.6 billion to 1, a number preserved in the cosmic microwave background radiation that will form hundreds of thousands of years later. The universe now contains the raw materials for atomic nuclei, protons and neutrons suspended in a bath of radiation, electrons, positrons, and neutrinos. The temperature continues to fall, the density continues to drop, and the cosmos prepares for its next transformation. In a few minutes, when the temperature drops below 1 billion Kelvin, these protons and neutrons will begin to fuse, forging the first atomic nuclei in the process called Big Bang nucleosynthesis. But for now, in this microsecond-old universe, the quark-gluon plasma has given way to a hot gas of hadrons, and the building blocks of matter have taken their first stable form. The hadrons drift through the expanding cosmos, protons and neutrons suspended in a sea of radiation so intense that light itself cannot travel more than a fraction of a millimeter before scattering. But hidden within this apparent symmetry lies one of the deepest mysteries in all of physics, a puzzle that makes the very existence of matter possible. For every proton that survives in this microsecond-old universe, For every neutron that will eventually find its way into an atomic nucleus, there should have been an equal and opposite antiparticle. And yet, the universe is made almost entirely of matter. The antimatter is gone, annihilated in the first moments after reheating, leaving behind only this slight excess that will become every galaxy, every star, every planet, and every atom in the cosmos. The asymmetry is extraordinarily small. For every billion antiquarks that formed in the reheating phase, there were 1,000,000,001 quarks. This difference of 1 part in a billion, this tiny imbalance in the fundamental symmetry of nature, is the reason anything exists at all. When quarks met antiquarks in the hot plasma, they annihilated into pure energy, gamma rays that added to the already intense radiation field. Pair by pair, matter and antimatter destroyed each other, converting their mass back into photons according to Einstein's equation relating energy and mass. But because there was 1 extra quark for every billion pairs, 1 survivor for every billion annihilations, a residue of matter remained after the antimatter was exhausted. This process, called baryogenesis, must have occurred somewhere between the end of inflation and the formation of stable hadrons, in the temperature range between 10 to the 15th and 10 to the 12th Kelvin. The exact mechanism remains one of the great unsolved problems in physics, a question that connects particle physics to cosmology in the most fundamental way. What broke the symmetry? What process favored matter over antimatter by precisely 1 part in a billion? The Russian physicist Andrei Sakharov identified 3 conditions that any successful theory of baryogenesis must satisfy. First, there must exist processes that violate baryon number conservation, reactions that can create more baryons than antibaryons, or vice versa. Second, the fundamental forces must violate both charge conjugation symmetry and the combined symmetry of charge conjugation and parity, meaning that the laws of physics must distinguish between matter and antimatter in some subtle way. Third, these processes must occur out of thermal equilibrium, because in perfect equilibrium, any process that creates excess baryons would be exactly balanced by the reverse process that destroys them. The standard model of particle physics satisfies all 3 Sakharov conditions, but only barely. Baryon number violation occurs through a quantum mechanical process called a Sphaleron transition, where the electroweak vacuum can tunnel between states with different baryon numbers. These transitions are exponentially suppressed at low temperatures, but become significant when the universe is hot enough, above approximately 100 gigaelectronvolts, or about 10 to the 15th Kelvin. The standard model also violates CP symmetry, the combined symmetry of charge conjugation and parity, through the complex phase in the quark mixing matrix. And the expanding universe provides the out-of-equilibrium conditions as it cools through the electroweak phase transition. But here the standard model fails. The amount of CP violation measured in particle physics experiments is far too small to explain the observed matter-antimatter asymmetry. The baryon-to-photon ratio predicted by standard model baryogenesis is approximately 10 to the power of -18, while the observed ratio is approximately 6 times 10 to the power of -10, a discrepancy of 8 orders of magnitude. Something beyond the standard model must be responsible for the excess matter in the universe. Theorists have proposed numerous mechanisms to explain this cosmic imbalance. One possibility is leptogenesis, where the asymmetry first appears in the lepton sector, among electrons and neutrinos, and is later converted to a baryon asymmetry through sphaleron processes. This scenario requires the existence of very heavy right-handed neutrinos, particles with masses around 10 to the power of 10 to 10 to the power of 15 gigaelectron volts that would have been produced in the hot early universe and decayed asymmetrically, producing slightly more leptons than antileptons. The sphalerons, active at temperatures above the electroweak scale, would then partially convert this lepton asymmetry into a baryon asymmetry, preserving a combination of baryon and lepton number while violating each individually. Another possibility is electroweak baryogenesis, which requires new physics at the electroweak scale to enhance the CP violation and strengthen the electroweak phase transition. In the Standard Model, the transition from the symmetric electroweak phase to the broken phase where the W and Z bosons acquire mass is a smooth crossover, not a sharp phase transition. But if new particles exist with masses around 100 to 1000 gigaelectron volts, they could make this transition strongly first order, proceeding through the nucleation and expansion of bubbles of the broken phase within the symmetric phase. CP violating interactions at the bubble walls could then generate the baryon asymmetry as particles scatter from the expanding boundaries. The Affleck-Dine mechanism offers yet another route to baryogenesis, one that operates during or shortly after inflation. In supersymmetric theories, scalar fields carrying baryon number can acquire large expectation values during inflation, storing baryon number in a coherent field configuration. As the universe reheats and these fields begin to oscillate and decay, they release their stored baryon number into ordinary quarks and antiquarks, with the asymmetry determined by CP violating terms in the scalar potential. This mechanism can naturally produce the observed baryon to photon ratio for a wide range of parameters. Whatever the mechanism, the result is the same. By the time the universe is a few microseconds old, the antimatter has been annihilated, and only the slight excess of matter remains. The energy released in these annihilations adds to the radiation field, contributing to the enormous number of photons that will eventually become the cosmic microwave background. For every baryon that survives, approximately 1.6 billion photons are produced, a ratio that encodes the magnitude of the original asymmetry, and remains frozen into the universe as it expands and cools. The surviving baryons, these protons and neutrons that emerged from the quark-gluon plasma, now drift through a universe still dominated by radiation. The temperature has fallen to approximately 10 to the 10th power Kelvin, about 1,000 times hotter than the core of the Sun, and the cosmos is approximately 1 second old. At this temperature, neutrinos are just beginning to decouple from the rest of matter, their interaction cross-section falling as the universe expands until they can no longer maintain thermal equilibrium. These relic neutrinos will stream freely through the cosmos from this moment forward, carrying information about the universe at 1 second old, just as the cosmic microwave background will carry information about the universe at 380,000 years. The neutron-to-proton ratio is now being set by the weak nuclear force. Neutrons can convert to protons by emitting an electron and an antineutrino, and protons can convert to neutrons by capturing electrons or emitting positrons. At high temperatures, these reactions proceed rapidly in both directions, maintaining an equilibrium ratio determined by the mass difference between neutrons and protons, approximately 1.293 mega-electron-volts. As the temperature drops below about 10 to the 10th Kelvin, these reactions slow and eventually freeze out, leaving the neutron-to-proton ratio fixed at approximately 1 neutron for every 6 protons. But neutrons are unstable. A free neutron will decay into a proton, an electron, and an antineutrino with a half-life of approximately 610 seconds, about 10 minutes. The universe is now in a race against time. If the temperature drops slowly enough for nucleosynthesis to begin before too many neutrons decay, these neutrons can be incorporated into stable atomic nuclei where they are protected from decay. If the expansion is too slow, the neutrons will all decay, and the universe will contain only hydrogen, no helium, no heavier elements forged in the first few minutes. The cosmos continues to cool, the radiation continues to redshift, and the surviving baryons await their next transformation. In approximately 3 minutes, when the temperature falls below 1 billion Kelvin, protons and neutrons will begin to fuse, forging deuterium, helium-3, helium-4, and traces of lithium-7 in the process called Big Bang nucleosynthesis. The abundances of these light elements, measured in the oldest stars and the most pristine gas clouds, will provide one of the most precise confirmations of the hot Big Bang model, a fossil record of the universe when it was mere minutes old. The temperature falls. At 3 minutes and 46 seconds after the beginning, the cosmos has cooled to approximately 1 billion Kelvin, roughly 60 times hotter than the core of the Sun. At this temperature, something remarkable becomes possible. Deuterium, the fragile isotope of hydrogen containing 1 proton and 1 neutron, can finally survive. Before this moment, deuterium faced immediate destruction. The photons permeating the universe carried enough energy to shatter any deuterium nucleus the instant it formed, a process called photodisintegration. A deuterium nucleus has a binding energy of only 2.22 million electron volts, and in the earlier, hotter universe, countless photons exceeded this threshold. For every baryon in the cosmos, there exist approximately 1.6 billion photons, and even when only a tiny fraction of these photons carry sufficient energy, the deuterium bottleneck remains firmly closed. But as the universe expands, the photons lose energy. Their wavelengths stretch with the fabric of space itself, and the high-energy tail of the thermal distribution shrinks. When the temperature drops below the critical threshold, deuterium production finally outpaces deuterium destruction. The bottleneck opens, and nucleosynthesis begins in earnest. Protons and neutrons collide and stick. A proton captures a neutron, releasing a gamma ray with an energy of 2.22 million electron volts, and deuterium forms. This reaction proceeds rapidly because the strong nuclear force, which binds nucleons together, operates on timescales of 10 to the minus 23rd seconds. Within moments, the universe fills with deuterium nuclei, each one a stepping stone to heavier elements. Deuterium does not accumulate. Almost as quickly as it forms, it undergoes further reactions. A deuterium nucleus collides with a proton, producing helium-3 and a gamma ray. Alternatively, two deuterium nuclei collide, yielding either helium-3 plus a neutron or tritium plus a proton. Tritium, the radioactive isotope of hydrogen with one proton and two neutrons, has a half-life of 12.3 years in isolation, but in the furnace of the early universe, it reacts almost immediately. Tritium captures a deuterium nucleus and produces helium-4 plus a neutron, or it captures a proton and produces helium-4 plus a gamma ray. Helium-3 follows similar pathways. It can capture a neutron to become tritium, or it can collide with another helium-3 nucleus to produce helium-4 plus 2 protons. All roads lead to helium-4, the most stable light nucleus, with a binding energy of 28.3 million electron volts. This exceptional stability means that once helium-4 forms, it resists further disruption. The universe is building a stockpile of helium that will persist for billions of years. The neutron-to-proton ratio at this moment determines the final helium abundance. When nucleosynthesis begins, approximately 1 neutron exists for every 7 protons. Nearly all of these neutrons will be incorporated into helium-4 nuclei, because helium-4 contains equal numbers of protons and neutrons and represents the most energetically favorable configuration. If 1 neutron exists for every 7 protons, then for every 16 nucleons, 2 are neutrons and 14 are protons. These 2 neutrons combine with 2 protons to form 1 helium-4 nucleus, leaving 12 protons as free hydrogen. The mass fraction of helium-4 is therefore approximately 4 divided by 16, or 25%. This prediction, derived from the physics of the early universe, matches observations with remarkable precision. Measurements of helium abundance in the oldest, most metal-poor regions of the cosmos consistently yield values between 23 and 25% by mass. This agreement represents one of the great triumphs of Big Bang cosmology, a quantitative confirmation that the universe was once hot enough and dense enough for nuclear fusion to occur throughout all of space simultaneously. The reactions do not stop at helium-4, but they slow dramatically. Helium-4 is exceptionally stable, and there is no stable nucleus with 5 nucleons. When helium-4 captures a proton, the resulting lithium-5 decays in approximately 10 to the minus 22 seconds. When helium-4 captures a neutron, the resulting helium-5 is equally unstable. This mass-5 gap creates a barrier that primordial nucleosynthesis cannot easily cross. A small amount of lithium-7 forms through an indirect pathway. Helium-4 captures a tritium nucleus to produce lithium-7 plus a gamma ray, or helium-3 captures helium-4 to produce beryllium-7, which later decays to lithium-7 by capturing an electron. The predicted primordial lithium abundance is approximately 1 lithium-7 atom for every 10 billion hydrogen atoms, a trace so faint that detecting it requires observing the oldest, most pristine stars in the galaxy. Here, cosmology encounters one of its persistent puzzles. Observations of ancient stars consistently show lithium abundances 2 to 3 times lower than the predicted primordial value. This lithium problem remains unresolved. Some physicists propose that the oldest stars have destroyed their primordial lithium through internal mixing processes. Others suggest that the physics of the early universe contains subtleties not yet understood, perhaps involving new particles or modified nuclear reaction rates. The discrepancy is small in absolute terms, but significant in its implications, a reminder that even the most successful theories may harbor incomplete understanding. Beryllium and boron form in even smaller quantities, their abundances suppressed by the mass 5 and mass 8 gaps. Beryllium-8, if it formed, would decay into 2 helium-4 nuclei in approximately 10 to the minus 16 seconds. Without stable stepping stones, the synthesis of carbon, nitrogen, and oxygen must wait for a different furnace, one that will not exist for hundreds of millions of years. The window of nucleosynthesis is brief. By approximately 20 minutes after the beginning, the temperature has fallen below 300 million Kelvin, and the density has dropped to the point where nuclear reactions effectively cease. The Coulomb barrier, the electromagnetic repulsion between positively charged nuclei, becomes insurmountable at these lower energies. Protons and helium nuclei drift past each other without fusing, their thermal velocities insufficient to overcome their mutual repulsion. The universe emerges from this epoch with a specific chemical composition. By mass, approximately 75% is hydrogen-1, ordinary protons, approximately 25% is helium-4. Deuterium survives at a level of approximately 25 parts per million relative to hydrogen, a fossil abundance that provides one of the most sensitive probes of the cosmic baryon density. Helium-3 persists at roughly 10 parts per million. Lithium-7, despite the observational puzzle, exists at approximately 1 part per 10 billion. These abundances are frozen into the fabric of the cosmos. Unlike the elements forged in stellar cores, which are recycled through generations of stars, the primordial abundances reflect conditions in the first 20 minutes of cosmic history. Measuring them in the most ancient and unprocessed environments allows cosmologists to peer back to an epoch when the entire observable universe was a nuclear reactor, when the laws of physics were writing the initial conditions for all chemistry to come. The deuterium abundance proves particularly valuable. Deuterium is fragile, easily destroyed in stellar interiors, but never produced in significant quantities by any known astrophysical process after the Big Bang. Every deuterium nucleus observed today is either primordial or has been destroyed and not replaced. By measuring deuterium in the most pristine gas clouds, illuminated by distant quasars and observed through absorption spectroscopy, cosmologists can determine the cosmic baryon density with precision. The current best measurements indicate approximately 4.9% of the universe's total energy density consists of ordinary baryonic matter, a value consistent with independent measurements from the cosmic microwave background. The helium abundance tells a complementary story. Because nearly all neutrons end up in helium-4, the helium mass fraction depends sensitively on the neutron-to-proton ratio at the onset of nucleosynthesis, which in turn depends on the expansion rate of the universe during the first few minutes. If additional particle species existed, contributing to the energy density and accelerating the expansion, more neutrons would survive to form helium. Measurements of primordial helium thus constrain the number of light particle species, providing evidence that exactly 3 types of neutrinos exist, consistent with laboratory experiments at particle accelerators. The cosmos continues to expand and cool. The nuclear fires have burned out, leaving behind a plasma of hydrogen and helium nuclei, electrons, photons, and neutrinos. The photons scatter continuously off the free electrons, maintaining thermal equilibrium and preventing light from traveling freely. The universe remains opaque, a fog of radiation and matter intertwined. The fog persists for hundreds of thousands of years. The universe expands, the wavelengths of photons stretch, and the temperature drops with mathematical precision according to the inverse relationship between scale factor and temperature. At 10,000 years after the beginning, the cosmos has cooled to approximately 28,000 Kelvin, still far too hot for electrons to bind permanently to nuclei. The photons carry enough energy to ionize any atom that dares to form, stripping electrons away within fractions of a second. But the expansion is relentless, and time favors patience. The density of matter and radiation evolves differently as space stretches. Radiation density decreases faster than matter density because photon wavelengths lengthen in addition to the dilution from expanding volume. At approximately 47,000 years after the beginning, a quiet transition occurs. The energy density of matter, dominated by hydrogen and helium nuclei, along with the mysterious dark matter that outweighs ordinary atoms by a factor of 5, surpasses the energy density of radiation. The universe enters the matter-dominated era, and the expansion rate changes subtly, governed now primarily by the gravitational pull of mass rather than the pressure of light. The plasma continues to cool. At 100,000 years, the temperature has fallen to approximately 6,000 Kelvin, comparable to the surface of a yellow dwarf star. The photons still possess enough energy to ionize hydrogen, whose binding energy is 13.6 electron volts, corresponding to a photon wavelength of 91.2 nanometers in the ultraviolet. But the distribution of photon energies follows a thermal spectrum, a Planck curve with a long tail extending to higher energies. Even when the average photon energy drops below the ionization threshold, the high-energy tail contains enough ultraviolet photons to keep the hydrogen ionized. The critical factor is the ratio of photons to baryons. For every proton or neutron in the universe, there exist approximately 1.6 billion photons. This enormous ratio means that even when only a tiny fraction of photons carry ionizing energies, their sheer numbers overwhelm the attempts of electrons to settle into bound states. An electron captured by a proton is almost immediately knocked free by another photon from the vast sea of radiation. The temperature must fall considerably below the naive ionization threshold before recombination can proceed. The calculation involves the Saha equation, which describes the equilibrium between ionized and neutral states as a function of temperature and density. The equation reveals that recombination occurs not at a single temperature, but gradually, as the ionization fraction drops from near unity to near zero over a range of temperatures. At approximately 300,000 years after the beginning, the temperature reaches 4,000 Kelvin. The ionization fraction begins to drop measurably. electrons start to find permanent homes in the ground states of hydrogen atoms, emitting photons as they cascade down through the energy levels. But these recombination photons can themselves ionize other atoms, creating a complex feedback loop that slows the process. The universe solves this problem through a subtle mechanism. When an electron falls directly to the ground state of hydrogen, it emits a Lyman alpha photon with an energy of 10.2 electron volts. This photon is immediately absorbed by another hydrogen atom, exciting it and potentially ionizing it. The net effect is zero progress toward neutrality, but electrons can also reach the ground state through the 2-photon decay channel from the 2s state, emitting a pair of lower energy photons that cannot ionize hydrogen. This slow leak allows recombination to proceed, atom by atom, over tens of thousands of years. At 380,000 years after the beginning, the temperature has fallen to approximately 3,000 Kelvin, and the ionization fraction drops below 1%. The mean free path of photons, which had been measured in centimeters when the plasma was fully ionized, suddenly extends to cosmic scales. The universe becomes transparent. This moment is called the surface of last scattering, though it is not a surface in any geometric sense. It is a time, a cosmic epoch when photons decouple from matter and begin their long journey through the expanding universe. The photons that scatter for the last time at this epoch carry information about the conditions of the universe at that moment, frozen into their distribution of temperatures and wavelengths. The cosmic microwave background radiation is born. The photons released at recombination have a nearly perfect thermal spectrum, a black-body distribution with a temperature of approximately 3,000 Kelvin at the moment of release. As the universe expands, the wavelengths of these photons stretch proportionally with the scale factor. The temperature of the radiation drops inversely with the scale factor, maintaining the black-body form, but shifting the peak wavelength from the near-infrared at the time of recombination to the microwave band today. The present temperature of the cosmic microwave background is 2.7255 Kelvin, measured with extraordinary precision by satellite observatories. This temperature corresponds to a peak wavelength of approximately 1.9 millimeters in the microwave region of the electromagnetic spectrum. The radiation fills all of space uniformly, arriving from every direction with the same intensity to 1 part in 100,000. But it is the tiny deviations from perfect uniformity that carry the deepest information. The temperature fluctuations in the cosmic microwave background, measured at the level of tens of microkelvins, represent the seeds of all cosmic structure. These fluctuations originate from quantum variations during inflation, stretched to macroscopic scales, and imprinted on the matter radiation plasma. Regions slightly denser than average appear slightly cooler because photons lose energy climbing out of gravitational potential wells. Regions slightly less dense appear slightly warmer. The pattern of fluctuations is not random noise. It contains a characteristic angular scale of approximately 1 degree, corresponding to the sound horizon at the time of recombination. Before decoupling, the plasma supports acoustic oscillations, pressure waves driven by the competition between gravitational collapse and radiation pressure. Regions that have completed exactly half an oscillation compressed to maximum density, appear as peaks in the temperature power spectrum. Regions caught at the rarefaction phase appear as troughs. The first acoustic peak occurs at an angular scale of about 1 degree, corresponding to a physical size of approximately 450,000 light-years at the time of recombination. This scale represents the distance that sound waves could travel in the plasma from the beginning of the universe until recombination, the sound horizon. The precise angular size of this feature depends on the geometry of the universe, and measurements confirm that space is flat to within 1%, consistent with the predictions of inflation. Higher acoustic peaks reveal additional information. The ratio of odd to even peaks constrains the baryon density, because baryons add inertia to the oscillations, enhancing compression phases relative to rarefaction phases. The damping of peaks at small angular scales results from photon diffusion during recombination, as photons random walk out of small-scale perturbations, erasing structure below a characteristic length called the Silk damping scale. The cosmic microwave background also carries polarization information. The scattering of photons off electrons produces linear polarization, with the polarization direction related to the local temperature gradient. The pattern of polarization divides into two types, called E-modes and B-modes, analogous to the curl-free and divergence-free components of a vector field. E-mode polarization arises from density perturbations and has been measured in detail. B-mode polarization can arise from gravitational waves, potentially providing direct evidence of inflation, though the primordial signal remains elusive, obscured by foreground contamination from galactic dust. The universe after recombination is a dark place. The cosmic microwave background photons, once visible light, have red-shifted into the infrared and continue their journey toward the microwave band. No stars exist yet to provide new sources of illumination. The hydrogen and helium atoms drift through the expanding void, cooling as the universe stretches, their thermal motion slowing as the temperature drops. This is the beginning of the cosmic dark ages, an epoch lasting hundreds of millions of years, during which the universe contains matter but no light sources. The atoms settle into their ground states, the residual ionization fraction dropping to approximately 1 part in 10,000 as the last free electrons find their atomic homes. The cosmic microwave background continues to cool, its photons stretching ever longer, carrying their frozen record of the young universe across the growing emptiness. The darkness deepens as the cosmic microwave background fades from visibility, shifting through the infrared toward longer and longer wavelengths. The universe enters an epoch of profound stillness. The temperature continues its relentless decline, dropping below 3,000 Kelvin, then below 1,000, then below 100. By the time 50 million years have passed since the release of the primordial light, the cosmic background radiation has cooled to approximately 50 Kelvin, colder than any natural environment on Earth today, colder than the liquid nitrogen used in laboratories, approaching the temperature of deep space as we measure it in the modern era. The hydrogen and helium atoms that emerged from recombination now drift through this cooling void in near-perfect darkness. No photons of visible light traverse the cosmos. The only radiation present consists of the ever-stretching remnants of the primordial fireball. Photons whose wavelengths have grown so long that they carry almost no energy, invisible to any hypothetical observer, detectable only as a faint warmth against the absolute zero of empty space. The universe has become, in a very real sense, blind to itself. Yet within this darkness, structure continues to grow. The density fluctuations imprinted during inflation, those quantum whispers stretched to cosmic scales, have been growing since the moment of recombination. Before the atoms formed, radiation pressure prevented matter from collapsing under its own gravity. Photons scattered so frequently off free electrons that any attempt by matter to clump was immediately smoothed out by the outward pressure of light. But now, with the photons decoupled and streaming freely through space, matter is free to fall. The process begins slowly, almost imperceptibly. In regions where the primordial density was slightly higher than average, perhaps by 1 part in 100,000, gravity exerts a marginally stronger pull. Atoms drift toward these overdense regions at speeds measured in centimeters per second, velocities so small that a human walking pace would seem like a supersonic jet by comparison. But the universe is patient, and time stretches ahead in quantities that dwarf human comprehension. Dark matter, that invisible scaffolding comprising approximately 84% of all matter in the cosmos, leads the collapse. Unlike ordinary atoms, dark matter particles do not interact with light and never experienced the radiation pressure that held baryonic matter at bay. Dark matter began collapsing immediately after inflation ended, and by the time of recombination, it had already formed a cosmic web of filaments and nodes, a skeleton of gravitational potential wells waiting to be filled. Now, as the ordinary matter decouples from radiation, it falls into these pre-existing structures like water flowing into valleys carved by ancient rivers. The mathematics of gravitational collapse in an expanding universe follows precise rules. In a region of slight overdensity, the gravitational attraction between particles works against the universal expansion. If the overdensity is sufficient, gravity eventually wins, and the region stops expanding, reaches a maximum size, and begins to contract. This turnaround occurs at different times for different scales. Smaller structures, containing less mass, collapse first. Larger structures, spanning greater distances, take longer to overcome the cosmic expansion. During the Dark Ages, the first structures to collapse are dark matter halos, with masses comparable to small dwarf galaxies, perhaps 1 million to 100 million times the mass of the Sun. These halos form at the intersections of the cosmic web, where filaments of dark matter converge. The ordinary matter, the hydrogen and helium gas, follows the dark matter into these potential wells, heating as it falls. This heating occurs through a process called adiabatic compression. As gas falls into a gravitational well, it gains kinetic energy, and this kinetic energy manifests as thermal motion, as heat. The temperature of the infalling gas rises to several hundred Kelvin, then to 1,000 Kelvin in the densest regions. This may seem warm compared to the cosmic background, but it remains far too cold to trigger nuclear fusion. The gas cannot yet form stars. It simply accumulates in the dark matter halos, swirling and settling, radiating away its heat through the emission of infrared photons from molecular hydrogen. molecular hydrogen, H2, plays a crucial role during this epoch. Individual hydrogen atoms, in their ground state, cannot efficiently radiate energy at these temperatures. The quantum mechanical selection rules forbid the transitions that would allow a hydrogen atom to emit a photon and cool down. But when two hydrogen atoms bond together to form a molecule, new vibrational and rotational energy states become available. These molecular states allow the gas to radiate energy and cool, shedding the heat gained during gravitational collapse. The formation of molecular hydrogen occurs through a delicate chain of chemical reactions. First, a free electron attaches to a hydrogen atom, forming a negatively charged hydrogen ion, H-. This ion then encounters a neutral hydrogen atom and transfers its extra electron, creating a hydrogen molecule and releasing the original electron to participate in further reactions. The process is slow, limited by the scarcity of free electrons in the mostly neutral post-recombination universe. The residual ionization fraction, that 1 part in 10,000 of electrons that never found atomic homes, becomes essential for the chemistry that will eventually enable star formation. As the Dark Ages progress, the cosmic web becomes increasingly pronounced. Simulations of structure formation reveal a universe that resembles a three-dimensional foam, with vast, empty voids surrounded by walls and filaments of matter, and dense nodes at the intersections where the first galaxies will eventually form. The voids expand as matter drains from them into the surrounding structures. The filaments stretch across tens of millions of light years, rivers of dark matter and gas flowing towards the nodes of highest density. The temperature of the cosmic microwave background continues to fall. At 100 million years after the Big Bang, it has dropped to approximately 60 Kelvin. At 200 million years, it approaches 30 Kelvin. The universe grows colder and darker with each passing epoch, the primordial light fading like the last embers of a dying fire. Yet within the dark matter halos, the gas grows denser and hotter, a reversal of the cosmic trend, pockets of warmth forming against the backdrop of universal cooling. The first protogalactic structures take shape during this era, clouds of gas and dark matter with masses ranging from millions to billions of solar masses. These structures are not yet galaxies in any recognizable sense. They contain no stars, no heavy elements, no planets. They are simply accumulations of primordial material, hydrogen and helium, in roughly the 3-to-1 ratio established during nucleosynthesis, laced with trace amounts of deuterium and lithium, falling together under the patient pull of gravity. The density at the centers of these proto-galaxies reaches values of perhaps 100 atoms per cubic centimeter, still far more tenuous than the best laboratory vacuums on Earth, but millions of times denser than the average cosmic density. At these concentrations, molecular hydrogen formation accelerates and the cooling rate increases. The gas begins to fragment, breaking into smaller clumps as regions of slightly higher density cool faster and contract more rapidly than their surroundings. This fragmentation process continues hierarchically. Large clouds break into smaller clouds, which break into still smaller clumps, each generation denser and hotter at its core than the last. The minimum mass of these fragments is set by the gene's mass, a quantity determined by the balance between thermal pressure and gravitational attraction. For gas cooling through molecular hydrogen emission at temperatures of a few hundred Kelvin, the gene's mass is approximately 1,000 solar masses, far larger than the mass of a typical star in the modern universe. The Dark Ages draw toward their end as these dense cores approach the conditions necessary for gravitational collapse to run away. The temperature at the center of the densest clumps rises past 1,000 Kelvin, then past 2,000. The molecular hydrogen begins to dissociate, breaking back into individual atoms, absorbing energy, and temporarily halting the temperature rise. But gravity continues its inexorable work, compressing the gas further, driving the density higher. Somewhere in the universe, in a dark matter halo that has grown particularly massive, in a gas cloud that has cooled particularly efficiently, the first core reaches a critical threshold. The density climbs past 10 billion atoms per cubic centimeter. The temperature soars past 10,000 Kelvin. The hydrogen becomes fully ionized once more, not by the primordial fireball, but by the heat of gravitational compression. And still the collapse continues, accelerating now, the core shrinking from light years to astronomical units, to solar radii in a cosmic eye blink. The Dark Ages end not with a gradual brightening, but with a sudden ignition. After perhaps 200 million years of darkness, the first star is born. The ignition is unlike anything the universe has witnessed since the first seconds of existence. Deep within the collapsing core, where densities have climbed past 100 billion atoms per cubic centimeter and temperatures have exceeded 10 million Kelvin, protons begin to overcome their mutual electromagnetic repulsion. The strong nuclear force, dormant since the epoch of primordial nucleosynthesis some 200 million years earlier, awakens once more. Hydrogen fuses into helium, and for the first time since the cosmos was 3 minutes old, nuclear fire burns. This first star is a monster by any standard the universe will later establish. The primordial gas from which it forms contains no carbon, no oxygen, no iron, none of the elements that will eventually allow gas clouds to cool efficiently and fragment into smaller pieces. Without these coolants, the collapsing cloud cannot shed its heat quickly enough to break apart. The result is a single, massive object that continues to accrete material from its surroundings with voracious efficiency. The star that emerges from this process contains perhaps 100 solar masses, possibly 300, perhaps even more. Some theoretical models suggest that the very first stars could have reached 500 or even 1,000 times the mass of the Sun, though such extreme objects would have lived lives measured in hundreds of thousands of years rather than millions. The surface of this primordial giant blazes at temperatures exceeding 100,000 Kelvin, roughly 17 times hotter than the surface of the Sun. At such temperatures, the star emits most of its radiation in the ultraviolet and extreme ultraviolet portions of the spectrum, wavelengths so energetic that they ionize hydrogen atoms on contact. The luminosity is staggering. A single population 3-star of 300 solar masses would outshine the Sun by a factor of 10 million, pouring energy into the surrounding darkness at a rate of approximately 4 times 10 to the 33rd watts. The nuclear reactions that power this brilliance follow a chain that begins with the proton-proton process, the same fusion pathway that operates in the core of the Sun. 4 hydrogen nuclei combine through a series of intermediate steps to produce 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and approximately 26.7 million electron volts of energy. But in these massive primordial stars, the core temperatures quickly climb high enough to activate a more efficient process. At temperatures above 15 million Kelvin, the carbon-nitrogen-oxygen cycle becomes the dominant energy source, even though the star initially contains no carbon, nitrogen, or oxygen. The resolution to this apparent paradox lies in the triple alpha process. As helium accumulates in the stellar core from hydrogen fusion, the temperature and density eventually reach the threshold, where 3 helium-4 nuclei can fuse to form carbon-12. This requires temperatures of approximately 100 million Kelvin and densities of roughly 100,000 grams per cubic centimeter. Once even trace amounts of carbon exist, the CNO cycle can operate, using carbon as a catalyst to convert hydrogen to helium far more efficiently than the proton-proton chain. The energy production rate of the CNO cycle scales as the 16th power of temperature, making it extraordinarily sensitive to conditions in the stellar core. The structure of a population 3 star differs fundamentally from later stellar generations. The core is convective, churning and mixing like a pot of boiling water, transporting freshly synthesized helium outward and bringing fresh hydrogen fuel inward. This convective mixing extends through a significant fraction of the star's mass, ensuring that a large reservoir of hydrogen remains available for fusion. The outer envelope, by contrast, is radiative, with energy transported outward by photons that scatter countless times before reaching the surface. The opacity of this primordial material is lower than in metal-enriched stars, allowing radiation to escape more readily and contributing to the extreme luminosity. The stellar wind that streams from the surface carries mass away at rates that may reach 10 to the -5 solar masses per year, stripping perhaps 10 to 20% of the star's initial mass over its brief lifetime. This wind is driven by radiation pressure, the momentum of photons pushing against atoms in the outer atmosphere. The wind velocity reaches thousands of kilometers per second, and the material it carries spreads outward into the surrounding medium, beginning the slow process of chemical enrichment that will eventually transform the composition of the cosmos. Within the core, the nuclear burning proceeds through stages that compress into a tiny fraction of cosmic time. Hydrogen fusion dominates for perhaps 2 million years, converting the core to helium, while the star maintains its position on what astronomers will later call the main sequence. When the hydrogen fuel in the core is exhausted, gravitational contraction resumes, heating the core until helium fusion ignites. The triple alpha process converts helium to carbon, and subsequent alpha captures produce oxygen-16 and neon-20. This helium-burning phase lasts perhaps 300,000 years. The subsequent stages accelerate dramatically. Carbon fusion ignites when the core temperature reaches approximately 600 million Kelvin, producing neon, sodium, and magnesium. This phase lasts roughly 1,000 years. Neon burning follows at 1.2 billion Kelvin, lasting perhaps 1 year. Oxygen fusion occurs at 1.5 billion Kelvin, persisting for several months. Finally, silicon burning commences at approximately 2.7 billion Kelvin, and in a single day, the core converts silicon to iron group elements, primarily iron 56 and nickel 56. Iron represents the end of the fusion road. The binding energy per nucleon reaches its maximum at iron 56, meaning that no further energy can be extracted by fusing iron into heavier elements. The core, now composed primarily of iron, can no longer generate the thermal pressure needed to support the overlying stellar mass. The collapse that follows is catastrophic and nearly instantaneous. In less than 1 second, the iron core implodes from a radius of several thousand kilometers to a radius of roughly 10 kilometers, reaching densities of several 100 million tons per cubic centimeter. The implosion halts when the core reaches nuclear density, approximately 2.3 times 10 to the 17th kilograms per cubic meter. At this point, the strong nuclear force provides a repulsive pressure that stops the collapse and causes the infalling material to bounce. A shock wave forms and propagates outward through the still collapsing outer layers. Neutrinos produced in enormous quantities as protons and electrons combine to form neutrons carry away approximately 3 times 10 to the 46th joules of energy in a burst lasting roughly 10 seconds. A small fraction of this neutrino energy is deposited in the material behind the shock, reviving it and driving the explosion that tears the star apart. The supernova that results is among the most energetic events the universe has yet produced. The kinetic energy of the ejected material reaches approximately 10 to the 44th joules, equivalent to the total energy output of the Sun over 10 billion years, released in a matter of seconds. The peak luminosity may briefly exceed 10 billion solar luminosities, making the dying star visible across cosmological distances. The light curve rises and falls over weeks to months, powered initially by the shock-heated ejector and later by the radioactive decay of nickel 56 to cobalt 56 to iron 56. The explosion disperses the products of stellar nucleosynthesis into the surrounding medium. Carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, and iron stream outward at velocities of thousands of kilometers per second. These elements, forged in the nuclear furnace of the first star and scattered by its violent death, will eventually be incorporated into the next generation of stars and the planets that form around them. The oxygen atoms that will one day fill the atmospheres of habitable worlds, the iron that will form their cores, the carbon that will serve as the backbone of organic molecules, all trace their origins to moments like this, to the deaths of massive stars in the early universe. Some population 3 stars may have met different fates. Those with masses between roughly 140 and 260 solar masses likely experienced pair instability supernovae, a distinct explosion mechanism triggered when the core temperature exceeds approximately 3 billion Kelvin. At such temperatures, the photons in the stellar core become energetic enough to spontaneously convert into electron-positron pairs. This process removes pressure support from the core, triggering a runaway collapse that ignites explosive oxygen and silicon burning. The nuclear energy released exceeds the gravitational binding energy of the star, and the entire object is obliterated, leaving no compact remnant behind. These explosions may have been 10 to 100 times more energetic than ordinary core collapse supernovae. Stars more massive than approximately 260 solar masses may have collapsed directly to black holes, with the core imploding so rapidly that no explosion occurs. The outer layers fall inward and are swallowed, leaving behind a black hole of perhaps 100 solar masses or more. These primordial black holes may have served as seeds for the supermassive black holes that will eventually anchor the centers of galaxies. The first stars do not burn alone for long. Within a few million years of the first ignition, similar collapses occur in dark matter halos throughout the observable universe. Each ignition marks the birth of another population 3 star, another nuclear furnace converting hydrogen to helium and helium to heavier elements. The darkness that has persisted for 200 million years begins to retreat, pushed back by the ultraviolet radiation streaming from these primordial giants. The cosmic dawn has begun. The ultraviolet photons stream outward from each population 3 star at 300,000 kilometers per second, carrying energies of 13.6 electron volts or greater. This is the ionization threshold of hydrogen, the precise energy required to strip an electron from a neutral hydrogen atom and convert it into a free proton and a free electron. As these photons encounter the neutral hydrogen that fills intergalactic space, they are absorbed, and the atoms they strike are torn apart. Around each massive star, a bubble of ionized gas begins to form. The boundary of this bubble, called an ionization front, expands outward at velocities that depend on the density of the surrounding medium and the luminosity of the central source. In the low-density voids between dark matter halos, where hydrogen atoms are separated by distances of several meters on average, the ionization front can advance at speeds approaching 10,000 kilometers per second. In denser regions, where gas has begun to accumulate around nascent structures, the front slows, sometimes to mere hundreds of kilometers per second, as each photon must ionize more atoms per unit distance traveled. The temperature inside these ionized bubbles rises dramatically. Neutral hydrogen at the end of the Dark Ages has cooled to temperatures of just a few tens of Kelvin, approaching absolute zero. But when ionization occurs, the liberated electrons carry kinetic energy imparted by the absorbed photons. This energy thermalizes through collisions, heating the ionized gas to temperatures between 10,000 and 30,000 Kelvin. The intergalactic medium transforms from a cold, neutral fog into a hot, ionized plasma, and this transformation is irreversible on cosmological timescales. The process begins approximately 200 million years after the Big Bang, when the first population 3 stars ignite. But the universe is vast, and individual stars, even stars of 100 solar masses or more, can only ionize finite volumes. A single population 3 star burning for 3 million years might ionize a region spanning a few 100,000 light-years in diameter. The observable universe at this epoch stretches across 40 million light-years. Complete reionization will require not one star, but millions upon millions of ionizing sources working in concert across hundreds of millions of years. The ionized bubbles grow and begin to overlap, Where two bubbles meet, the ionization fronts merge, and the combined region becomes a single, larger bubble. The topology of reionization resembles the growth of bubbles in a foam or the percolation of water through a porous medium. Initially, the ionized regions are isolated islands in a sea of neutral hydrogen. As more stars form and more bubbles expand, the islands grow and connect, forming chains and networks of ionized gas. Eventually, the neutral regions become the isolated islands, shrinking pockets of cold hydrogen surrounded by an interconnected web of hot plasma. The sources of ionizing radiation evolve as reionization proceeds. The first population 3 stars are extraordinarily luminous but short-lived, burning through their hydrogen fuel in 3 to 5 million years before exploding or collapsing. Their supernovae scatter heavy elements into the surrounding gas, enriching it with carbon, oxygen, silicon, and iron at abundances of perhaps 1/10,000th the solar value. This enrichment, though slight, fundamentally changes the physics of subsequent star formation. Gas enriched with heavy elements can cool more efficiently than pristine hydrogen and helium. Carbon and oxygen atoms, even at trace abundances, provide additional channels for radiating away thermal energy. Molecular species like carbon monoxide form and emit photons at infrared wavelengths, allowing gas clouds to shed heat and collapse at lower masses. The second generation of stars, called Population 2, forms from this enriched material. These stars are smaller than their Population 3 predecessors, with typical masses between 1 and 50 times the mass of the Sun. They are less luminous individually, but they form in greater numbers, and they live longer. A Population 2 star of 10 solar masses burns for approximately 30 million years, 10 times longer than a comparable Population 3 star. A star of 1 solar mass can burn for 10 billion years, long enough to still be shining in the present-day universe. The shift from Population 3 to Population 2 star formation increases the total number of ionizing photons produced per unit of gas converted into stars. More importantly, it distributes the ionizing radiation over longer timescales, sustaining the ionization of intergalactic hydrogen even as individual stars die. By 400 million years after the Big Bang, the first primitive galaxies have begun to assemble. These are not the grand spiral structures that will characterize the mature universe, but irregular collections of gas and stars, spanning perhaps a few thousand light years and containing stellar masses equivalent to a few million suns. Each proto-galaxy hosts ongoing star formation, producing a continuous supply of ionizing photons. The ionized bubbles surrounding these early galaxies grow to diameters of millions of light years, and the overlap between neighboring bubbles accelerates. Observations of distant quasars provide evidence for the timeline of reionization. Quasars are supermassive black holes actively consuming gas, and their accretion disks emit light across the electromagnetic spectrum. When quasar light travels through neutral hydrogen, it is absorbed at specific wavelengths corresponding to the Lyman series transitions of hydrogen atoms. The pattern of absorption reveals the ionization state of the intergalactic medium along the line of sight. Quasars observed at redshifts greater than 6, corresponding to times less than 1 billion years after the Big Bang, show evidence of significant neutral hydrogen absorption. Their spectra display the Gunn-Peterson trough, a complete suppression of light at wavelengths shorter than the Lyman alpha transition, indicating that the intergalactic medium still contained substantial neutral hydrogen. Quasars at redshifts below 6 show progressively less absorption, indicating that reionization was largely complete by approximately 1 billion years after the Big Bang. The cosmic microwave background also records the signature of reionization. As the universe reionizes, free electrons become available to scatter CMB photons through a process called Thomson scattering. This scattering slightly suppresses the amplitude of CMB temperature fluctuations and generates a characteristic polarization pattern. Measurements by the Planck satellite indicate an optical depth to reionization of approximately 0.054, corresponding to a mean reionization redshift of approximately 7.7, or about 700 million years after the Big Bang. The end of reionization marks a fundamental transition in the optical properties of the universe. Before reionization, the intergalactic medium was opaque to ultraviolet light. Photons with energies above 13.6 electron volts were absorbed within short distances, their energy consumed in ionizing neutral atoms. After reionization, the intergalactic medium becomes transparent. Ultraviolet photons can travel across billions of light years, their paths unimpeded by neutral hydrogen. The universe, which has been foggy since the release of the cosmic microwave background, finally clears. This transparency is not absolute. The ionized intergalactic medium still absorbs photons at specific wavelengths, particularly those corresponding to transitions of residual neutral hydrogen and ionized helium. Helium, with its higher ionization potential of 24.6 electron volts for the first electron and 54.4 electron volts for the second, remains partially neutral even after hydrogen reionization is complete. The full ionization of helium requires harder ultraviolet photons, which become abundant only when quasars reach their peak activity approximately 2 to 3 billion years after the Big Bang. The thermal state of the intergalactic medium after reionization reflects the violence of the process. Gas that has been photoionized retains a temperature of approximately 10,000 to 20,000 Kelvin for billions of years. This temperature is maintained by a balance between photoheating from the ultraviolet background radiation and cooling through the expansion of the universe and through atomic processes. The hot intergalactic medium resists gravitational collapse into small dark matter halos, suppressing the formation of dwarf galaxies and shaping the distribution of visible matter in the cosmos. The ionizing background radiation that maintains this state is produced collectively by all the galaxies and quasars in the universe. Each source contributes photons that travel through intergalactic space until they are absorbed by a hydrogen atom or redshifted below the ionization threshold by cosmic expansion. The intensity of this background radiation has been measured through observations of the proximity effect around quasars and through the statistics of absorption lines in quasar spectra. At redshift 3, approximately 2 billion years after the Big Bang, the ionizing background corresponds to roughly 100,000 photons per square centimeter per second per steradian at the hydrogen ionization edge. The transition from a neutral to an ionized universe is complete. The cosmic dawn, which began with the ignition of the first stars, has given way to full daylight. The intergalactic medium, once a cold and opaque fog, has become a hot and transparent plasma. Light can now travel freely across the cosmos, and the universe has entered the epoch of galaxy formation in earnest. The transparent universe becomes a crucible for structure. With the intergalactic medium now ionized and permeable to light, the gravitational scaffolding of dark matter continues its patient work of assembly. Halos merge with halos. Small structures fall into larger ones. The process follows a pattern that cosmologists call hierarchical clustering, and it operates according to precise mathematical rules encoded in the initial density fluctuations that emerged from inflation. At 500 million years after the Big Bang, the typical dark matter halo hosting active star formation contains roughly 1 billion solar masses of material. This is still modest by later standards. The Milky Way's halo will eventually reach 2 trillion solar masses. But these early structures represent the seeds from which all future galaxies will grow. The merger rate is ferocious. Computer simulations tracking the evolution of representative cosmic volumes show that a typical halo experiences between 2 and 5 major mergers during the first billion years, where a major merger involves a companion at least 1/3 as massive as the primary. The baryonic matter within these halos responds to the mergers with complex dynamics. When two gas-rich protogalaxies collide, their dark matter halos pass through each other like interpenetrating swarms of bees, interacting only through gravity. But the gas behaves differently. Shock waves form at the interface where two gas clouds meet, heating the material to temperatures of 10 million Kelvin or higher. This shock-heated gas radiates energy through thermal Bremsstrahlung and atomic line emission, losing thermal support and settling toward the center of the merged system. The cooling time depends critically on the gas density and temperature. For primordial gas at 10 million Kelvin with a density of 1 particle per cubic centimeter, the cooling time is approximately 300 million years. But as the gas compresses toward the center of the halo, the density rises and the cooling time shortens dramatically. At 100 particles per cubic centimeter, the cooling time drops to 3 million years. At 10,000 particles per cubic centimeter, it falls to 30,000 years. This runaway cooling funnels gas toward the centers of merged halos, building dense reservoirs of fuel for star formation. The geometry of this infall creates distinctive structures. Gas that cools slowly tends to settle into rotating disks, supported against further collapse by angular momentum. Gas that cools rapidly falls directly toward the center in cold streams, filamentary flows that penetrate deep into the halo without shock heating. Simulations of galaxy formation at high redshift reveal that these cold flows dominate the mass accretion in halos below about 10 to the 12th solar masses. The streams carry gas at temperatures of 10,000 to 30,000 Kelvin, dense enough to self-shield against the ionizing background radiation that pervades intergalactic space. The star formation that results from this gas accumulation differs from the pristine population 3 mode. By 700 million years after the Big Bang, the interstellar medium within protogalaxies has been enriched with heavy elements from the first generations of supernovae. Metallicities have risen to between 1,000th and 100th of the solar value in the densest regions. This seemingly small contamination transforms the physics of stellar birth. Carbon and oxygen atoms provide cooling channels that did not exist in primordial gas. The fine structure transition of singly ionized carbon at 158 micrometers and the forbidden line of neutral oxygen at 63 micrometers allow gas to radiate away thermal energy at temperatures below 10,000 Kelvin, where hydrogen cooling becomes inefficient. The minimum temperature that a collapsing cloud can reach drops from roughly 200 Kelvin in primordial gas to 10 or 20 Kelvin in metal-enriched material. Lower temperatures mean lower thermal pressures, which in turn mean that smaller masses can overcome pressure support and collapse. The characteristic stellar mass shifts accordingly. Instead of the 100 solar mass giants of population 3, the second generation of stars, population 2, forms with a mass distribution much closer to what is observed in the present-day universe. The initial mass function, describing how stellar masses are distributed at birth, develops a peak near half a solar mass and a power law tail extending to high masses with a slope of approximately -2.3. For every star of 10 solar masses, there are roughly 200 stars of 1 solar mass and 2,000 stars of 1/10 solar mass. This shift has profound consequences for the luminosity and longevity of early galaxies. Population 3 stars burned through their nuclear fuel in 2 to 3 million years. Population 2 stars spanning a range of masses include many that will shine for billions or even trillions of years. A half-solar mass star, burning hydrogen at a leisurely rate, has a main sequence lifetime exceeding 40 billion years, longer than the current age of the universe. These low-mass stars, once formed, become permanent fixtures of the cosmos. The spatial distribution of star formation within early protogalaxies is clumpy and irregular. Unlike the smooth spiral patterns of mature disk galaxies, these young systems resemble collections of dense star-forming knots embedded in diffuse gas. Each knot contains between 1 million and 100 million solar masses of stars, spanning physical sizes of 100 to 500 parsecs. The knots form where gas densities exceed the threshold for gravitational instability, typically around 100 particles per cubic centimeter in the presence of a modest metallicity. Observations with the James Webb Space Telescope have revealed these clumpy structures in galaxies at redshifts between 6 and 10, corresponding to ages between 500 million and 900 million years after the Big Bang. The rest-frame ultraviolet light from these systems, red-shifted into the near-infrared by cosmic expansion, shows irregular morphologies with multiple bright regions separated by darker lanes. Spectroscopic measurements detect emission lines from ionized oxygen and hydrogen, confirming active star formation at rates of 10 to 100 solar masses per year, 10 to 100 times higher than the present-day Milky Way. The stellar populations within these early galaxies are young by definition. At 700 million years after the Big Bang, no star can be older than 700 million years. The light is dominated by massive O and B type stars, with surface temperatures exceeding 20,000 Kelvin, radiating predominantly in the ultraviolet. The integrated spectrum of a young stellar population shows a steep blue continuum, strong hydrogen emission lines from surrounding ionized gas, and absorption features from stellar winds in the most massive stars. As these galaxies age, their stellar populations evolve. The most massive stars explode as supernovae within a few million years, enriching the interstellar medium with heavy elements and injecting kinetic energy that drives turbulence and outflows. Stars of intermediate mass, between 1 and 8 solar masses, evolve more slowly, spending tens of millions to billions of years on the main sequence, before expanding into red giants and eventually shedding their outer layers as planetary nebulae. The integrated color of a galaxy gradually reddens as the blue massive stars die, and the longer-lived red stars come to dominate the light. The chemical enrichment proceeds in a characteristic pattern. Core collapse supernovae, arising from stars more massive than 8 solar masses, produce primarily oxygen, neon, magnesium, and silicon, the so-called alpha elements, synthesized through successive stages of helium capture. These supernovae occur promptly, within 30 million years of a star formation episode. Type 1a supernovae, arising from white dwarf binary systems, produce primarily iron peak elements and occur with a delay of 100 million to several billion years. The ratio of alpha elements to iron in a stellar population therefore encodes information about the timescale of its formation. Observations of the oldest stars in the Milky Way's halo reveal enhanced alpha to iron ratios, indicating that they formed rapidly from gas enriched primarily by core collapse supernovae. These ancient stars, with ages approaching 13 billion years, are the surviving low-mass members of the early stellar generations that populated the first galaxies. Their chemical abundances serve as fossil records of nucleosynthesis in the young universe. The assembly of larger structures continues through gravitational attraction. By 1 billion years after the Big Bang, the most massive halos have grown to contain 100 billion solar masses of dark matter, comparable to the mass of a present-day dwarf galaxy. Within these halos, multiple protogalactic fragments orbit and occasionally merge, their stellar populations mixing while their gas reservoirs combine and trigger new bursts of star formation. The process is violent and chaotic, yet the end result is the gradual construction of ever larger galactic systems. The violence of early assembly gradually subsides into a more measured rhythm. As the universe ages past its first billion years, the chaotic mergers and rapid collapses give way to a sustained epoch of stellar activity that will persist for more than 10 billion years. This is the stelliferous era, the age when nuclear fusion operates at its peak efficiency across countless galaxies, steadily converting primordial hydrogen and helium into the heavier elements that will eventually constitute planets, oceans, and living organisms. The transformation is quantitative as well as qualitative. At the peak of cosmic star formation, occurring roughly 3 billion years after the Big Bang, when the universe has cooled to approximately 15 Kelvin in its background radiation, galaxies collectively produce stars at a rate of roughly 10 times higher than they do today. Massive spiral galaxies churn out dozens of solar masses worth of new stars each year, their disk structures stabilized by angular momentum and threaded with dense molecular clouds where gravitational collapse proceeds continuously. The star formation rate density across the observable universe reaches approximately 0.15 solar masses per year per cubic megaparsec, a figure that will decline steadily over the following 10 billion years as gas reservoirs deplete. Within each forming star, the same fundamental process unfolds regardless of mass or location. Gravitational contraction heats the core until temperatures exceed 10 million Kelvin, at which point proton-proton fusion ignites in stars below approximately 1.3 solar masses, while the carbon-nitrogen-oxygen cycle dominates in more massive objects. The physics is identical to what occurred in population 3 stars, but the chemical environment has changed dramatically. The interstellar medium now contains trace amounts of carbon, oxygen, nitrogen, and heavier elements, seeded by previous stellar generations. These metals, as astronomers call all elements heavier than helium, alter the cooling properties of collapsing gas clouds and enable the formation of lower-mass stars that could not have existed in the pristine early universe. The mass distribution of newly formed stars follows a pattern known as the initial mass function. For every star born with 10 solar masses, approximately 100 stars form with 1 solar mass, and roughly 1,000 stars form with 1/10 of a solar mass. This distribution, first characterized by astronomer Edwin Salpeter in 1955, appears remarkably consistent across different galaxies and cosmic epochs, suggesting that the fragmentation physics of molecular clouds operates according to universal principles. The consequence is that the universe produces vastly more low-mass stars than high-mass stars, and since low-mass stars live far longer, the stellar population becomes increasingly dominated by small, dim, long-lived objects as cosmic time advances. The lifetime of a star depends on its mass raised to a negative power. A star of 10 solar masses exhausts its core hydrogen in approximately 20 million years. A star like the Sun persists for 10 billion years. A red dwarf of 0.1 solar masses will continue fusing hydrogen for more than 10 trillion years, far exceeding the current age of the universe. This inverse relationship between mass and lifetime creates a temporal layering effect in galactic stellar populations. The massive blue stars that illuminate spiral arms and ionize surrounding nebulae are always young, having formed within the past few tens of millions of years. The intermediate mass yellow and orange stars represent a broader age range. The dim red dwarfs include objects that formed in the earliest epochs of galactic assembly and continue burning today. Their nuclear fires so slow and efficient that they have consumed only a small fraction of their fuel over 13 billion years. The nucleosynthesis occurring within stellar cores follows distinct pathways depending on stellar mass. In stars below approximately 8 solar masses, fusion proceeds through hydrogen burning, then helium burning, which produces carbon and oxygen through the triple alpha process. This process requires 3 helium-4 nuclei to combine into carbon-12, a reaction that depends critically on a nuclear resonance predicted by Fred Hoyle in 1954 and subsequently confirmed experimentally. Without this resonance, carbon production would be negligible, and the universe would lack the foundation for organic chemistry. The existence of this resonance is sometimes cited as evidence of fine-tuning in physical constants, though the interpretation remains debated. Stars above 8 solar masses continue fusion beyond helium burning, their cores reaching temperatures sufficient to ignite carbon at approximately 600 million Kelvin, neon at 1.2 billion Kelvin, oxygen at 1.5 billion Kelvin, and silicon at 2.7 billion Kelvin. Each successive burning stage proceeds faster than the last, because the energy yield per reaction decreases while the luminosity requirements increase. A 20 solar mass star burns hydrogen for 8 million years, helium for 1 million years, carbon for 1,000 years, neon for approximately 1 year, oxygen for several months, and silicon for merely 1 day. The final day of silicon burning produces an iron core, and here fusion reaches its terminus. Iron 56 has the highest binding energy per nucleon of any nucleus, meaning that neither fusion nor fission of iron releases energy. The core, suddenly unable to generate the pressure needed to support the overlying stellar layers, collapses. The collapse proceeds at a significant fraction of the speed of light. Within milliseconds, the iron core compresses from a radius of several thousand kilometers to a neutron star of merely 10 kilometers, reaching densities of 10 to the 17th kilograms per cubic meter. The infalling outer layers rebound off this incompressible neutron core, generating a shock wave that propagates outward and tears the star apart in a core collapse supernova. The explosion releases approximately 10 to the 46th power joules of energy, most of it carried away by neutrinos, with only about 1% emerging as kinetic energy of the expanding debris and visible light. For a few weeks, a single supernova can outshine its entire host galaxy. The supernova explosion accomplishes 2 critical functions in cosmic chemical evolution. First, it disperses the elements synthesized during the star's lifetime: carbon, oxygen, neon, magnesium, silicon, and sulfur, into the surrounding interstellar medium. Second, the extreme conditions of the explosion itself drive rapid neutron capture processes that synthesize elements heavier than iron. The R process, occurring in the neutron-rich environment of the collapsing core or in the merger of neutron stars, produces approximately half of all elements heavier than iron, including gold, platinum, and uranium. The S process, occurring more slowly in the helium-burning shells of asymptotic giant branch stars, produces the other half through gradual neutron capture interspersed with beta decay. The enrichment of the interstellar medium proceeds cumulatively over billions of years. Each stellar generation incorporates the metals produced by previous generations, processes them through nuclear burning, and returns an enriched mixture to the surrounding gas. The metallicity of the universe, measured as the mass fraction of elements heavier than helium, increases from essentially 0 at the Big Bang to approximately 2% in the present-day Sun. This 2% represents the accumulated nuclear ash of roughly 10 billion years of stellar activity across hundreds of billions of galaxies. The spatial distribution of metals is not uniform. Galactic centers, where star formation has been most intense and sustained, achieve higher metallicities than galactic outskirts. Massive elliptical galaxies, formed through multiple mergers of smaller systems, contain stellar populations with a range of metallicities reflecting their complex assembly histories. Dwarf galaxies, with their shallower gravitational potential wells, lose enriched gas more easily to supernova-driven outflows and consequently maintain lower metallicities. The intergalactic medium itself becomes enriched over time as galactic winds carry metals beyond the boundaries of individual galaxies, seeding the cosmic web with trace amounts of heavy elements. The enrichment of the cosmos with heavy elements is only half the story of stellar evolution. Every star that has forged metals in its core must eventually exhaust its nuclear fuel and confront the fundamental question of gravitational collapse. The answer to that question depends almost entirely on mass, and the universe sorts its dying stars into three distinct categories of remnant, each representing a different solution to the battle between gravity and the quantum mechanical forces that resist compression. Stars like the Sun, and indeed the vast majority of stars that have ever formed, follow the gentlest path to stellar death. When a star of roughly 1 solar mass exhausts the hydrogen in its core after approximately 10 billion years on the main sequence, the core contracts and heats while the outer layers expand into a red giant phase. Helium fusion ignites in the core at temperatures exceeding 100 million Kelvin, converting helium into carbon and oxygen through the triple alpha process. But for stars below roughly 8 solar masses, the core never achieves the 600 million Kelvin threshold required to fuse carbon. Instead, the star sheds its outer layers in a planetary nebula, exposing the dense, degenerate core beneath. This remnant is a white dwarf, and its properties are extraordinary. A typical white dwarf contains roughly 60% of the original star's mass, compressed into a sphere approximately the size of Earth, with a radius of perhaps 6,000 kilometers. The resulting density reaches approximately 1 million grams per cubic centimeter, meaning a teaspoon of white dwarf material would weigh several tons on Earth's surface. At such densities, matter enters a state called electron degeneracy, where the Pauli exclusion principle prevents electrons from occupying the same quantum state. This quantum mechanical pressure, rather than thermal pressure from nuclear fusion, supports the white dwarf against gravitational collapse. The physics of electron degeneracy imposes a strict upper limit on white dwarf mass. In 1930, Subramanian Chandrasekhar calculated that no white dwarf can exceed approximately 1.4 solar masses, a value now known as the Chandrasekhar limit. Beyond this mass, electron degeneracy pressure cannot withstand gravity, and the star must collapse further. This limit arises from relativistic effects. As the white dwarf mass increases, the electrons must move faster to provide sufficient pressure, eventually approaching the speed of light. At the Chandrasekhar limit, the electrons become relativistic, and additional mass causes collapse rather than equilibrium. Newly formed white dwarfs emerge from their planetary nebulae, with surface temperatures exceeding 100,000 Kelvin, glowing blue-white with thermal radiation. But without nuclear fusion to replenish their energy, white dwarfs can only cool. Their luminosity decreases as they radiate away their stored thermal energy into space. A white dwarf with an initial temperature of 100,000 Kelvin will cool to 10,000 Kelvin in roughly 1 billion years, and to 4,000 Kelvin in approximately 10 billion years. The cooling rate slows as the temperature drops, following a predictable trajectory that allows astronomers to use white dwarf temperatures as cosmic clocks. The interior structure of a cooling white dwarf undergoes remarkable transformations. As the temperature drops below approximately 10,000 Kelvin, the carbon and oxygen ions in the core begin to crystallize, forming a lattice structure similar to a diamond. This crystallization releases latent heat, temporarily slowing the cooling process. Over billions of years, the white dwarf's core solidifies from the center outward, eventually becoming a sphere of crystalline carbon and oxygen, surrounded by a thin atmosphere of hydrogen or helium. The oldest white dwarfs in this galaxy, formed from stars that died more than 10 billion years ago, have cooled to temperatures below 4,000 Kelvin and emit primarily in the infrared. Stars more massive than approximately 8 solar masses follow a dramatically different evolutionary path. These stars possess sufficient core temperatures to fuse carbon, then neon, then oxygen, then silicon, each stage proceeding more rapidly than the last as the energy yield per fusion reaction decreases. Silicon fusion, the final stage, converts silicon into iron and nickel in a matter of days. But iron represents the end of the fusion road. Iron has the most tightly bound nucleus of any element, and fusing iron absorbs energy rather than releasing it. The star has built an iron core that cannot generate the thermal pressure needed to support the overlying layers. The collapse, when it comes, is catastrophic. The iron core, typically containing roughly 1.4 solar masses compressed into a sphere the size of Earth, suddenly loses its pressure support. Gravity accelerates the collapse to velocities approaching 1/4 the speed of light. In less than 1 second, the core density increases from approximately 1 billion grams per cubic centimeter to over 100 trillion grams per cubic centimeter. At these densities, electrons are forced to combine with protons through inverse beta decay, producing neutrons and neutrinos. The neutrinos, carrying away roughly 99% of the gravitational binding energy released in the collapse, stream outward at nearly the speed of light. The collapsing core halts abruptly when it reaches nuclear density, approximately 230 million metric tons per cubic centimeter. At this point, the strong nuclear force and neutron degeneracy pressure provide sufficient resistance to stop the collapse. The core rebounds slightly, sending a shockwave outward into the still infalling outer layers. This shockwave, energized by neutrino heating and hydrodynamic instabilities, eventually breaks through the stellar envelope, producing a core-collapsed supernova with a luminosity of roughly 10 billion solar luminosities. The remnant left behind is a neutron star, an object of almost incomprehensible density. A typical neutron star contains between 1 and 2 solar masses compressed into a sphere only 20 kilometers in diameter. The density at the center exceeds 500 trillion grams per cubic centimeter, several times the density of an atomic nucleus. At such densities, the distinction between individual neutrons begins to blur, and the matter may exist in exotic phases, including superfluids, superconductors, and possibly quark matter in the innermost core. Neutron stars rotate rapidly, a consequence of angular momentum conservation during the collapse. A star that rotated once per month as a red supergiant will spin hundreds of times per second as a neutron star. This rotation, combined with intense magnetic fields reaching 1 trillion Gauss or more, produces beams of electromagnetic radiation that sweep through space like lighthouse beacons. When these beams intersect Earth's line of sight, astronomers detect pulsars, sources of precisely timed radio pulses that arrive with clockwork regularity. The Crab pulsar, remnant of a supernova observed in 1054 CE, rotates 30 times per second and has been slowing at a rate of approximately 38 nanoseconds per day as it radiates rotational energy. The upper mass limit for neutron stars, analogous to the Chandrasekhar limit for white dwarfs, lies somewhere between 2 and 3 solar masses, though the exact value remains uncertain due to incomplete understanding of matter at nuclear densities. This limit, sometimes called the Tolman-Oppenheimer-Volkoff limit, represents the maximum mass that neutron degeneracy pressure and nuclear forces can support against gravity. Beyond this limit, no known force can halt gravitational collapse. Stars that leave behind cores exceeding this limit, or neutron stars that accrete sufficient additional mass, collapse to form black holes. The collapse proceeds past nuclear density, past any conceivable form of matter, until all the mass concentrates at a mathematical point called the singularity. Surrounding this singularity is the event horizon, a boundary in space-time from which nothing, not even light, can escape. For a non-rotating black hole of 10 solar masses, the event horizon has a radius of approximately 30 kilometers, defined by the Schwarzschild radius formula. Black holes formed from stellar collapse typically range from roughly 3 to perhaps 100 solar masses, depending on the mass of the progenitor star and how much material falls back after the supernova explosion. The most massive stars, those exceeding perhaps 25 solar masses, may collapse directly to black holes without producing a visible supernova, as the shock wave fails to overcome the infalling material. These failed supernovae would appear as stars that simply vanish from the sky, leaving behind only darkness. The universe accumulates these stellar remnants over billions of years. White dwarfs, the most common endpoint, number in the hundreds of billions within the Milky Way alone. Neutron stars, formed only from the most massive progenitors, are rarer but still number in the hundreds of millions per galaxy. Stellar mass black holes, rarer still, may number in the tens of millions per galaxy. Each remnant represents the compressed legacy of a star that once shone, now existing in a state of permanent equilibrium, or, in the case of black holes, permanent isolation from the observable universe. These remnants persist as the universe continues its relentless expansion, and the conditions that once allowed stars to form gradually deteriorate across timescales that dwarf the current age of the cosmos by factors of 10,000. The cessation of star formation does not arrive as a sudden event, but as a slow exhaustion. Galaxies consume their reservoirs of cold molecular gas through ongoing stellar birth, and each generation of stars locks away hydrogen and helium in stellar cores or ejects it into the intergalactic medium at velocities exceeding the escape speed of their host galaxies. The Milky Way currently converts approximately 1 to 3 solar masses of gas into new stars each year, a rate that has already declined from its peak of 10 to 20 solar masses per year some 10 billion years ago. At current consumption rates, the galaxy's remaining gas supply of roughly 5 billion solar masses would sustain star formation for only another few billion years. But the actual timeline extends somewhat longer due to recycling from stellar winds and supernovae. By 100 billion years after the Big Bang, most spiral galaxies have exhausted their star-forming capacity. The cosmic star formation rate, which peaked around 3 billion years after the Big Bang at roughly 10 times its current value, has declined to less than 1% of that maximum. The universe at this epoch contains galaxies that are recognizably similar to those of today, but their stellar populations have aged uniformly toward the red end of the spectrum. The hot blue stars that once illuminated spiral arms have long since burned through their hydrogen and departed the main sequence, leaving behind populations dominated by red dwarfs and the cooling remnants of more massive progenitors. The red dwarfs become the primary sources of light in this aging cosmos. Stars with masses below approximately 0.25 solar masses burn their hydrogen so slowly that their main sequence lifetimes exceed 1 trillion years. A star of 0.1 solar masses, near the minimum mass required for sustained hydrogen fusion, possesses a theoretical main sequence lifetime of approximately 10 trillion years, roughly 700 times the current age of the universe. These dim furnaces, radiating at temperatures between 2,300 and 3,500 Kelvin, with luminosities less than 1% of the sun's output, become the dominant light sources as their more massive siblings fade into remnancy. The transition into what cosmologists term the degenerate era occurs around 10 to the 14th years after the Big Bang, 100 trillion years from now. At this epoch, even the longest-lived red dwarfs have begun to exhaust their hydrogen fuel. The last generation of main sequence stars, those born from the final wisps of molecular gas in the final episodes of star formation, complete their extraordinarily prolonged nuclear burning and contract toward the white dwarf state. The universe enters a phase where no new stars ignite and no fusion reactions illuminate the darkness. The physics of this transition follows directly from the properties of stellar structure. A red dwarf of 0.1 solar masses maintains itself against gravitational collapse through the pressure of its hot plasma, sustained by the energy released from proton-proton chain fusion in its core. The core temperature of such a star reaches approximately 4 million Kelvin, barely sufficient to overcome the electromagnetic repulsion between protons and allow quantum tunneling to initiate fusion. The reaction rate depends sensitively on temperature, scaling roughly as the fourth power of core temperature for the proton-proton chain. This extreme temperature sensitivity means that even small reductions in core temperature dramatically slow the fusion rate, extending the star's lifetime, but also dimming its output. As hydrogen depletes in the core, the star contracts slightly, raising its central temperature and temporarily accelerating fusion. But this negative feedback cannot continue indefinitely. When the core hydrogen mass fraction drops below approximately 10%, the star can no longer sustain the temperatures required for efficient fusion. The core contracts further, but unlike more massive stars, the red dwarf never achieves the 100 million Kelvin threshold required to ignite helium fusion. Instead, the star settles into a degenerate configuration supported by electron degeneracy pressure rather than thermal pressure. The resulting object is a helium white dwarf, distinct from the carbon-oxygen white dwarfs produced by Sun-like stars. These helium white dwarfs possess masses around 0.1 to 0.2 solar masses and radii comparable to Earth, giving them average densities of approximately 1 million grams per cubic centimeter. At such densities, the electrons in the stellar material are forced into a degenerate quantum state where the Pauli exclusion principle, rather than thermal motion, provides the pressure that resists gravitational collapse. The temperature of the white dwarf becomes largely irrelevant to its structural support, allowing it to cool indefinitely without contracting further. The cooling of white dwarfs follows a well-understood trajectory governed by the physics of heat transport through degenerate matter. A newly formed white dwarf with a surface temperature of 100,000 Kelvin radiates intensely in the ultraviolet, but this luminosity fades rapidly. The cooling rate depends on the white dwarf's mass, composition, and the properties of its thin, non-degenerate atmosphere. A typical carbon-oxygen white dwarf of 0.6 solar masses cools to a surface temperature of 4,000 Kelvin, dimmer than the faintest red dwarfs, within approximately 8 billion years. Continued cooling to 1,000 Kelvin requires roughly 100 billion years. By the time the degenerate era is fully established at 10 to the 14th years, the white dwarf population has cooled to temperatures approaching the cosmic microwave background, which itself has redshifted to a temperature of approximately 0.03 Kelvin. The white dwarfs have become black dwarfs in all but name, objects that emit virtually no detectable radiation and exist as cold, crystallized spheres of carbon and oxygen nuclei embedded in a rigid lattice of degenerate electrons. The crystallization process itself releases latent heat that temporarily slows the cooling. But by these late epochs, even this energy source has been exhausted. The galaxies that once blazed with the light of hundreds of billions of stars now drift through the expanding void as collections of dark remnants. Each galaxy contains its original complement of stellar mass objects, but these objects no longer shine. The stellar population has been transformed entirely into white dwarfs, neutron stars, and black holes, with brown dwarfs representing the only objects that never achieved fusion in the first place. The total mass in stellar remnants within a typical galaxy remains comparable to its original stellar mass, but the luminosity has dropped by factors exceeding 10 to the 20th power. The gravitational dynamics of these dark galaxies continue to evolve through processes that operate on timescales far exceeding the stellar era. Close encounters between remnants gradually redistribute energy through the system, a process known as dynamical relaxation. The relaxation timescale for a galaxy like the Milky Way, with its hundreds of billions of stellar remnants, exceeds 10 to the 19th years. Over such intervals, the galaxy slowly evaporates as repeated gravitational encounters eject the least massive members, while the more massive remnants sink toward the galactic center. The central supermassive black holes, which have grown to masses of billions of solar masses through accretion during the active galactic era, become the gravitational anchors around which the remaining bound remnants orbit. Occasional close passages send remnants plunging into the black hole or fling them into intergalactic space at velocities exceeding the galactic escape speed. The galaxy gradually loses mass to both processes, shrinking in both population and spatial extent as the eons accumulate. The process of gravitational evaporation unfolds through countless individual encounters, each one a subtle negotiation of energy and momentum between stellar remnants separated by light years of empty space. When two white dwarfs pass within a few astronomical units of each other, a rare event occurring perhaps once every million years in the outer reaches of a dying galaxy, they exchange gravitational energy in a dance governed by Newton's laws operating across timescales that would render any human clock meaningless. The mathematics of these encounters follows a statistical pattern first described by Subrahmanyan Chandrasekhar in the 1940s. In a system of gravitationally bound objects with different masses, energy tends to flow from the more massive bodies to the less massive ones through repeated gravitational interactions. This process, called dynamical relaxation, drives the system toward a state of energy equipartition where each object carries kinetic energy proportional to its mass. But stellar remnants cannot achieve true equipartition because the lightest objects gain enough velocity to escape the system entirely before equilibrium is reached. A white dwarf of half a solar mass, drifting through the outer halo of what was once a spiral galaxy, might experience a close passage with a neutron star of 1.4 solar masses. The encounter lasts only a few years as measured by the relative motion of the two objects, but the gravitational perturbation transfers energy from the more massive neutron star to the lighter white dwarf. The white dwarf gains perhaps 10 kilometers per second of velocity, a tiny increment, but one that accumulates over billions of such encounters across trillions of years. The escape velocity from a galaxy like the Milky Way, measured at a distance of 50,000 light-years from the center, is approximately 500 kilometers per second. A white dwarf starting with an orbital velocity of 200 kilometers per second must gain 300 additional kilometers per second through gravitational encounters before it can break free of the galactic potential well. At a rate of 10 kilometers per second per encounter, and with encounters occurring every million years on average, the process requires roughly 30 million encounters spanning 30 trillion years. But this simple calculation understates the complexity of the evaporation process. The galaxy itself is not static during these timescales. As lighter remnants escape, the total mass of the system decreases, which lowers the escape velocity and makes subsequent ejections easier. The remaining remnants sink deeper into the gravitational potential, increasing their orbital velocities and the frequency of close encounters. The process accelerates as it proceeds, following a characteristic timescale that depends on the initial mass and density of the stellar system. For a galaxy containing 100 billion stellar remnants with an average mass of half a solar mass, distributed across a volume 100,000 light-years in diameter, the evaporation timescale is approximately 10 to the 19th years, 10 quintillion years. or roughly 1 billion times the current age of the universe. During this interval, 90% of the galaxy's original stellar population will be ejected into intergalactic space, leaving behind only the most massive remnants clustered around the central, supermassive black hole. The ejected remnants do not simply vanish. They drift through the expanding universe as isolated objects, their velocities gradually redshifting as space itself stretches. A white dwarf ejected from the Milky Way at 600 kilometers per second will travel approximately 6 million light-years in 10 billion years, crossing the void between galaxies and potentially entering the gravitational influence of another galactic remnant. But by the time evaporation is complete, the expansion of the universe has carried neighboring galaxies far beyond any possibility of gravitational interaction. The Hubble parameter, which measures the expansion rate of the universe, has a current value of approximately 70 kilometers per second per megaparsec. This means that galaxies separated by 1 megaparsec, about 3.26 million light-years, are receding from each other at 70 kilometers per second due to cosmic expansion alone. At distances greater than the Hubble radius, approximately 14 billion light-years, the recession velocity exceeds the speed of light, and no signal or object can ever bridge the gap. As the universe ages into the degenerate era, the Hubble radius continues to grow, but the accelerating expansion driven by dark energy ensures that most galaxies have long since passed beyond any possibility of future contact. The ejected stellar remnants drift through an increasingly empty cosmos, their thermal radiation slowly fading as they cool toward the temperature of the cosmic microwave background, itself declining as the universe expands. The remnants that remain bound to the central black hole form a sparse halo, their orbits gradually circularizing through gravitational radiation and tidal interactions. A white dwarf in a highly elliptical orbit around a supermassive black hole of 4 million solar masses, similar to Sagittarius A star at the center of the Milky Way, will emit gravitational waves as it accelerates through the periapsis of its orbit. The energy carried away by these waves causes the orbit to shrink, drawing the white dwarf inexorably closer to the event horizon. The timescale for gravitational wave in spiral depends on the mass of the central black hole, the mass of the orbiting remnant, and the orbital parameters. For a white dwarf of half a solar mass in an orbit with a semi-major axis of 1 light-year around a 4 million solar mass black hole, the inspiral time exceeds 10 to the 25th years. But orbits with smaller semi-major axes or higher eccentricities decay much faster, and occasional gravitational encounters can scatter remnants onto plunging trajectories that carry them across the event horizon within a few orbital periods. Each remnant that falls into the central black hole adds to its mass and angular momentum, causing the event horizon to expand slightly. A supermassive black hole that began with 4 million solar masses might grow to 10 million solar masses by consuming the bound remnants of its host galaxy over the course of 10 to the 20th years. But this growth is slow compared to the feeding frenzy of the active galactic era, when gas accretion could add millions of solar masses in mere millions of years. The black hole also grows through mergers with other supermassive black holes. When two galaxies collide, an event that becomes increasingly rare as cosmic expansion separates galactic groups. Their central black holes eventually spiral together through dynamical friction against the surrounding stellar remnants. The final merger releases a burst of gravitational waves carrying energy equivalent to several percent of the combined black hole mass, rippling outward through space-time at the speed of light. The gravitational wave signal from a supermassive black hole merger has a characteristic frequency determined by the masses involved. Two black holes of 10 million solar masses each, merging at a separation of a few Schwarzschild radii, produce gravitational waves with frequencies around 10 to the minus 4 Hz, oscillations with periods of several hours. These waves stretch and compress space itself by fractional amounts of 10 to the minus 15 or smaller, detectable only by instruments spanning millions of kilometers. By the time the degenerate era reaches its full expression, the universe consists primarily of isolated black holes surrounded by sparse halos of bound remnants, interspersed with countless ejected white dwarfs, neutron stars, and stellar mass black holes drifting through the void. The cosmic web of dark matter filaments persists, but the baryonic matter that once traced these structures has largely dispersed or collapsed into compact objects. The temperature of the cosmic microwave background continues to fall as the universe expands. At 10 to the 14th years after the Big Bang, the CMB temperature has dropped to approximately 3 times 10 to the minus 11 Kelvin, 30 trillionths of a degree above absolute zero. This is far colder than any white dwarf, which retains internal heat from its formation and cools only gradually through photon emission from its surface. A white dwarf with a surface temperature of 4,000 Kelvin, typical of an old cooling remnant, radiates energy at a rate of approximately 10 to the 22nd watts. At this luminosity, the white dwarf will take roughly 10 to the 15th years to cool to 1,000 Kelvin, and another 10 to the 16th years to approach the temperature of the cosmic background. The cooling process slows as the temperature drops because the radiated power depends on the fourth power of temperature, following the Stefan Boltzmann law. The crystallization of white dwarf interiors adds another dimension to this cooling process. As a white dwarf cools below approximately 6,000 Kelvin, the carbon and oxygen ions in its core begin to arrange themselves into a crystalline lattice, releasing latent heat that temporarily slows the cooling rate. The crystallization front propagates outward from the center over billions of years, eventually converting the entire core into a quantum crystal where the ions are locked in place by their mutual electrostatic repulsion while degenerate electrons flow freely between them. The crystalline remnants of ancient stars drift through an emptiness that has grown beyond all previous comprehension. By the time the universe reaches an age of 10 to the 40th power years, a number so vast that writing it in standard notation would require a 1 followed by 40 zeros, the cosmos has undergone a transformation so complete that nothing from the stellar era would be recognizable. The galaxies that once blazed with the light of hundreds of billions of stars have long since dissolved, their gravitational bonds broken by the patient accumulation of stellar encounters that ejected remnant after remnant into the intergalactic void. What remains are black holes, These gravitational engines, forged in the depths of massive stars and grown through billions of years of mergers and accretion, have become the dominant structures in the universe. The supermassive black holes that once anchored galactic centers now drift through space as solitary monarchs, their masses ranging from millions to billions of solar masses. Around them, the cosmic microwave background radiation has redshifted to temperatures approaching 10 to the negative 30 Kelvin, so cold that the thermal energy of a single photon represents an almost inconceivable rarity. The transition into this era occurred gradually across timescales that make the entire stellar epoch seem like a brief flash. As galaxies lost their stellar remnants through gravitational evaporation, the central black holes consumed whatever material remained within their gravitational reach. Mergers between galaxies brought their central black holes together, and these cosmic collisions produced gravitational waves that rippled outward at the speed of light, carrying away energy and angular momentum until the black holes spiraled together and merged. Each merger created a larger black hole, and over trillions upon trillions of years, this process of hierarchical growth concentrated an ever greater fraction of the universe's baryonic mass into these gravitational wells. The physics of black holes becomes the dominant physics of this era. A black hole is defined by remarkably few properties: its mass, its angular momentum, and its electric charge. This simplicity, known as the no-hair theorem, means that all information about the matter that fell into the black hole, its composition, its temperature, its history, becomes inaccessible to the outside universe, encoded only in subtle correlations in the Hawking radiation that the black hole will eventually emit. The event horizon of a black hole marks the boundary beyond which nothing, not even light, can escape. For a non-rotating black hole with the mass of the Sun, this horizon would have a radius of approximately 3 kilometers. But the supermassive black holes that dominated this era have horizons measured in astronomical units. A black hole with a mass of 4 billion solar masses, comparable to the black hole that once resided at the center of the Milky Way's eventual merger remnant, would have an event horizon radius of roughly 12 billion kilometers, larger than the orbit of Neptune around the Sun. The space surrounding these black holes is not empty. Even in this late era, occasional remnants from the stellar epoch, white dwarfs that escaped ejection, neutron stars that wandered too close, fall toward the event horizons. As they approach, tidal forces stretch them along the radial direction and compress them perpendicular to it, a process called spaghettification. The material forms an accretion disk, heated by friction and gravitational compression to temperatures that briefly rival those of stellar cores. These transient flares of radiation represent the last gasps of matter before it crosses the event horizon and adds its mass to the black hole's gravitational dominion. The geometry of space-time near a black hole follows the predictions of general relativity with mathematical precision. Time itself flows differently in the intense gravitational field. A clock falling toward the event horizon would appear, to a distant observer, to slow down asymptotically, never quite reaching the horizon even as the infalling clock experiences only a finite proper time before crossing. This time dilation becomes extreme near the horizon, where the gravitational redshift stretches outgoing light to wavelengths approaching infinity. Rotating black holes, described by the Kerr metric, possess an additional structure called the ergosphere, a region outside the event horizon, where space-time itself is dragged along with the black hole's rotation so strongly that nothing can remain stationary relative to distant stars. Objects entering the ergosphere can extract rotational energy from the black hole through a process called the Penrose mechanism. Though in this late era, there is little matter remaining to exploit this possibility. The universe at 10 to the 40th years is dominated by these gravitational engines, but their reign is not eternal. The same quantum mechanics that governs the behavior of particles at the smallest scales also predicts that black holes cannot persist forever. Stephen Hawking's theoretical work in the 1970s revealed that black holes must radiate, not through any classical process, but through the quantum creation of particle-antiparticle pairs near the event horizon. This Hawking radiation emerges from the vacuum fluctuations that quantum field theory predicts occur throughout all of space. Near a black hole's event horizon, these fluctuations can be separated by the intense gravitational field. One particle falls into the black hole while its partner escapes to infinity, carrying away a tiny amount of the black hole's mass energy. The temperature of this radiation is inversely proportional to the black hole's mass, following the formula T equals h bar c cubed divided by 8 πgmk, where h bar is the reduced Planck constant, c is the speed of light, g is the gravitational constant, m is the black hole's mass, and k is Boltzmann's constant. For a stellar mass black hole of 10 solar masses, this temperature is approximately 6 times 10 to the negative 9th Kelvin, unimaginably cold, far below the current cosmic microwave background temperature of 2.7 Kelvin. Such a black hole would absorb more energy from the cosmic background than it radiates, actually growing rather than shrinking. But as the universe expands and the background radiation cools, eventually the Hawking temperature exceeds the ambient temperature, and the black hole begins its slow evaporation. The supermassive black holes that dominate this era have even lower Hawking temperatures. A black hole of 1 billion solar masses radiates at approximately 6 times 10 to the negative 17th Kelvin, a temperature so low that its thermal radiation consists almost entirely of gravitons and photons with wavelengths comparable to the black hole's event horizon itself. The power output of such radiation is minuscule, roughly 10 to the negative 30 watts for a stellar mass black hole, and even less for supermassive ones. Yet time is the great equalizer. Given sufficient duration, even the most massive black holes must eventually surrender their mass to the quantum vacuum. The evaporation timescale follows a cubic relationship with mass. A black hole takes approximately 10 to the 67th years, times the cube of its mass in solar masses to completely evaporate. A stellar mass black hole of 10 solar masses would require roughly 10 to the 67th years to evaporate, already a duration that dwarfs the current age of the universe by a factor of 10 to the 57th. A supermassive black hole of 10 billion solar masses would persist for 10 to the 97th years, approaching the time scale at which the final black holes will ultimately disappear. The universe during this black hole era is extraordinarily sparse. The average density of matter has fallen to levels where a single proton might occupy a volume larger than the current observable universe. The expansion of space has stretched the distances between black holes to scales measured in numbers that exceed human comprehension, separations of 10 to the 30th light years or more between neighboring gravitational engines. Light emitted from one black hole's accretion event would require longer than the current age of the universe multiplied by itself many times over to reach another. In this vast emptiness, the black holes drift according to their initial momenta, their paths curving only slightly in response to the gravitational influence of distant neighbors. Occasionally, over timescales measured in powers of 10 that strain mathematical notation, two black holes might approach closely enough to form a binary system, spiraling together over additional eons as gravitational wave emission carries away their orbital energy. These mergers produce brief bursts of gravitational radiation, ripples in space-time that propagate outward at the speed of light, carrying information about the collision across the expanding void. The entropy of the universe continues its inexorable increase throughout this era. Black holes represent the highest entropy configurations possible for a given amount of mass, with their entropy proportional to the surface area of their event horizons rather than their volume. A black hole of one solar mass contains an entropy of approximately 10 to the 77th in natural units, more than all the stars, planets, and gas in the current observable universe combined. The supermassive black holes that dominate this era represent entropy reservoirs of staggering magnitude, their event horizons encoding information about all the matter that has fallen across them throughout cosmic history. Yet even these supreme entropy reservoirs cannot persist forever. The same quantum mechanical principles that govern the behavior of particles at the smallest scales ensure that black holes, despite their seemingly absolute nature, must eventually surrender their mass to the surrounding vacuum. This process, first described theoretically by Stephen Hawking in 1974, transforms black holes from eternal prisons into slowly evaporating objects with finite lifespans measured in numbers that strain the limits of mathematical notation. The mechanism of Hawking radiation emerges from the restless nature of the quantum vacuum itself. Empty space, when examined at the Planck scale of 10 to the minus 35th meters, reveals itself to be anything but empty. Virtual particle-antiparticle pairs continuously fluctuate into existence, borrowing energy from the vacuum for brief intervals permitted by the Heisenberg uncertainty principle. These pairs typically annihilate within approximately 10 to the minus 21st seconds, returning their borrowed energy and leaving no permanent trace. But near the event horizon of a black hole, the intense curvature of space-time can separate these pairs before they recombine. When a virtual pair forms just outside the event horizon, tidal forces may pull the particles apart with sufficient violence that one member falls across the horizon while the other escapes to infinity. The escaping particle carries positive energy away from the black hole, while the infalling particle, from the perspective of a distant observer, carries negative energy into the interior. This negative energy contribution reduces the total mass of the black hole by a tiny amount, the mass equivalent of the escaping particle's energy divided by the speed of light squared. The black hole has effectively converted a small portion of its mass into radiation that streams away into the surrounding universe. The temperature of this radiation follows a precise inverse relationship with the black hole's mass. A black hole radiates as a nearly perfect thermal blackbody with a temperature given by Planck's constant times the speed of light, cubed, divided by 8 pi times the gravitational constant times the black hole's mass times Boltzmann's constant. For a black hole of 1 solar mass, this yields a temperature of approximately 60 nanokelvin, 60 billionths of a degree above absolute zero. This temperature is far colder than the current cosmic microwave background radiation at 2.7 Kelvin, meaning that solar mass black holes in the present universe actually absorb more energy from their surroundings than they emit. The supermassive black holes that dominate the universe during this era possess even lower temperatures. A black hole of 1 billion solar masses radiates at a temperature of merely 6 times 10 to the minus 17th Kelvin, a value so close to absolute zero that it defies intuitive comprehension. Such objects emit Hawking radiation at rates so slow that they gain mass from the cosmic microwave background far faster than they lose it through quantum emission. Only when the universe has expanded sufficiently for the background radiation to cool below these minuscule temperatures can the evaporation process truly begin. The cosmic microwave background temperature decreases in direct proportion to the scale factor of the universe, dropping by a factor of 2 each time the universe doubles in size. By the time the universe reaches an age of approximately 10 to the 19th years, the background radiation will have cooled to temperatures below those of stellar mass black hole remnants. By 10 to the 30th years, even the largest supermassive black holes will find themselves warmer than their surroundings, and the long process of evaporation will commence in earnest across all remaining gravitationally bound objects. The power output of a black hole through Hawking radiation scales inversely with the square of its mass. This relationship creates a runaway process. As a black hole loses mass, its temperature increases, causing it to radiate more intensely, which accelerates the mass loss further. The lifetime of a black hole scales with the cube of its initial mass, following a formula that yields approximately 10 to the 67th years for a solar mass black hole and 10 to the 100th years for a supermassive black hole of 10 billion solar masses. These timescales exceed any previously encountered in cosmic history by factors that render comparison meaningless. The current age of the universe, 13.8 billion years, represents merely 10 to the 10th years. The time required for a solar mass black hole to evaporate exceeds this by 57 orders of magnitude. If the entire history of the universe from the Big Bang to the present were compressed into a single second, the evaporation time of a stellar black hole would stretch across 30 billion trillion years. As the eons accumulate beyond 10 to the 40th years, the smallest black holes begin their final transformation. primordial black holes, if any survived from the early universe, with masses below approximately 10 to the 12th kilograms, would have already evaporated during earlier cosmic epochs. But the stellar mass remnants and supermassive giants persist, their event horizons shrinking imperceptibly as quantum fluctuations nibble away at their boundaries. The radiation emitted by an evaporating black hole carries away not only energy, but also information about the quantum states of particles that fell across the horizon throughout cosmic history. This information, encoded in subtle correlations between the emitted particles, gradually reconstructs a complete record of everything the black hole consumed. The process resolves what physicists once called the information paradox, the apparent conflict between quantum mechanics, which forbids the destruction of information, and the classical description of black holes as objects from which nothing can escape. The spectrum of Hawking radiation shifts toward higher energies as a black hole shrinks. A black hole that initially radiated primarily in radio wavelengths will eventually emit infrared photons, then visible light, then ultraviolet, then X-rays, and finally gamma rays as its temperature climbs through successive thresholds. In the final stages of evaporation, when a black hole has shrunk to masses comparable to large asteroids, its temperature reaches billions of Kelvin, and it radiates a brilliant burst of high-energy particles. The final moments of a black hole's existence unfold with increasing rapidity. When the mass drops below approximately 10 to the 9th kilograms, the remaining lifetime shrinks to less than a second. The temperature exceeds 10 to the 12th Kelvin, hot enough to produce electron-positron pairs, muons, pions, and eventually quarks and gluons in the emitted radiation. The black hole becomes a miniature particle accelerator, its Hawking radiation sampling the full spectrum of fundamental particles permitted by the Standard Model. The ultimate fate of an evaporating black hole remains partially uncertain, as the final Planck scale moments require a complete theory of quantum gravity that physicists have not yet achieved. When a black hole shrinks to the Planck mass of approximately 22 micrograms, its Schwarzschild radius equals the Planck length of 10 to the minus 35th meters, and the classical description of spacetime geometry breaks down entirely. The black hole may evaporate completely in a final burst of Planck energy particles, or it may leave behind a stable remnant of Planck mass, a question that current physics cannot definitively answer. Throughout this era, the universe continues its expansion, the distances between evaporating black holes growing at an accelerating rate, driven by dark energy. Each black hole exists in effective isolation, its Hawking radiation streaming outward into a void that grows emptier with each passing eon. The photons and particles emitted by evaporating black holes redshift as they travel through expanding space, their energies diminishing until they become indistinguishable from the thermal bath of the far future vacuum. The fate of matter itself hangs in the balance during these incomprehensible stretches of time. While black holes slowly surrender their mass to quantum radiation, the ordinary matter scattered throughout the cosmos, the protons and neutrons that constitute every atom, every remnant, every cold and drifting structure, faces its own quantum reckoning. The stability of the proton, long assumed to be absolute, reveals itself as merely provisional when examined across timescales that stretch beyond 10 to the 34th power years. The proton appears eternal by any human measure. Laboratory experiments have established that its half-life exceeds 10 to the 34 years, meaning that in a sample of protons observed for the entire current age of the universe, 13.8 billion years, not a single decay would be statistically expected. Yet the grand unified theories that attempt to merge the strong, weak, and electromagnetic forces into a single framework predict that protons are not truly stable. At energies approaching 10 to the 16th giga-electron volts, the grand unification scale, the distinctions between quarks and leptons blur, and processes forbidden at lower energies become possible. A proton composed of 2 up quarks and 1 down quark, bound by the strong force, can transform into lighter particles, a positron and a neutral pion, or perhaps a positive muon and a neutral pion, depending on the specific decay channel. The mechanism operates through the exchange of extraordinarily massive gauge bosons, the X and Y bosons predicted by grand unified theories, with masses around 10 to the 16th giga-electron volts, roughly 1 trillion times heavier than a proton. These particles cannot be produced in any conceivable accelerator, but quantum mechanics permits their fleeting virtual existence. For an infinitesimally brief moment, the energy uncertainty principle allows an X boson to materialize within the proton, mediating a transition that converts a quark into a lepton. The probability of this occurring in any given second is vanishingly small, roughly 1 chance in 10 to the 41st. But across timescales measured in 10 to the 34th years, even such improbable events become inevitable. The white dwarfs that survived the degenerate era, their carbon and oxygen nuclei locked in crystalline lattices at temperatures approaching absolute zero, begin to experience this quantum dissolution. Each nucleus contains protons, and each proton carries within it the seed of its own destruction. When a proton decays within a carbon nucleus, the nuclear structure destabilizes. The resulting positron annihilates with an electron, releasing 2 gamma-ray photons with energies of 511 kilo-electron volts each. The neutral pion decays almost instantaneously into 2 additional gamma rays. These photons deposit their energy into the surrounding crystal, producing a minuscule but measurable heating effect. A white dwarf of 1 solar mass contains approximately 10 to the 57th protons. If each proton has a half-life of 10 to the 37th years, then roughly 10 to the 20th protons decay each year, releasing about 10 to the 23rd electron volts of energy annually. This translates to a luminosity of approximately 10 to the negative 25th solar luminosities, utterly negligible by stellar standards, yet sufficient to maintain the white dwarf at a temperature slightly above the cosmic background radiation. The crystal lattice slowly erodes from within, its constituent nuclei gradually transmuting into lighter elements as protons vanish one by one. Neutron stars face a similar fate, though their extreme densities introduce additional complications. The neutrons packed into these stellar corpses are themselves unstable, decaying into protons, electrons, and antineutrinos, with a half-life of approximately 10 minutes when free. Within the neutron star, however, the Pauli exclusion principle and the filled electron energy states prevent most neutrons from decaying. There simply is no available quantum state for the resulting electron to occupy. But proton decay operates through different channels, and the protons present in the neutron star's crust and outer layers remain vulnerable. As these protons decay, the delicate balance of forces that maintains the neutron star's structure gradually shifts. The timescale for complete dissolution depends on the specific proton lifetime, which remains uncertain within several orders of magnitude. If protons decay with a half-life of 10 to the 34th years, a white dwarf would lose half its mass to decay products in that span. Still an almost inconceivable duration, but finite nonetheless. After 10 to the 35th years, only a quarter of the original protons would remain. After 10 to the 36th years, 1/8. The exponential nature of radioactive decay ensures that even the most massive structures eventually crumble to nothing. The decay products themselves undergo further transformations. The positrons emitted by proton decay annihilate with the electrons present in the stellar remnant, converting matter and antimatter into pure electromagnetic radiation. The gamma rays produced scatter through the remnant's interior, gradually thermalizing into lower energy photons that eventually escape into the surrounding void. The neutral pions decay into gamma rays within 10 to the -16 seconds of their creation, adding their energy to the thermal bath. Over time, the solid crystalline structure of a white dwarf transforms into an expanding cloud of photons, neutrinos, and the occasional surviving electron. The iron cores of ancient neutron stars, the densest concentrations of baryonic matter in the universe, persist longer than their less compressed cousins. The extreme gravitational binding energy of a neutron star, equivalent to roughly 10% of its rest mass, means that even as protons decay, the released energy must overcome a substantial gravitational potential before escaping. The neutron star shrinks as it loses mass, its gravitational field weakening proportionally. Eventually, when sufficient mass has been lost to decay, the remnant may no longer qualify as a neutron star at all, transitioning into an exotic object of uncertain composition. Throughout this era, the universe continues its accelerating expansion. The distances between dissolving remnants grow at rates that would have seemed absurd to earlier cosmic epochs. Structures that were once separated by megaparsecs now lie at distances measured in numbers that require scientific notation with exponents in the hundreds. The cosmic horizon, the boundary beyond which light emitted today will never reach us, contracts relative to the expanding space, isolating each dissolving remnant in its own private universe. The electrons that survive proton decay present their own puzzle. As the lightest charged particles, electrons cannot decay into anything lighter while conserving electric charge. If charge conservation holds absolutely, electrons may persist forever, drifting through the void as the last surviving representatives of the matter that once formed stars and galaxies. Their fate depends on physics beyond the standard model. Some theories predict that electrons, too, may eventually decay through processes involving virtual black holes or other exotic mechanisms, but such predictions remain highly speculative. The neutrinos released by various decay processes accumulate throughout this era, forming a diffuse background radiation even colder and more dilute than the cosmic microwave background. These ghostly particles, interacting only through the weak force, pass through the dissolving remnants without effect, carrying away energy and entropy into the expanding void. The universe's neutrino content grows steadily as matter converts itself into radiation, the total number of neutrinos eventually exceeding the number of photons by significant factors. By 10 to the 40th years, the proton decay process has reduced most baryonic structures to expanding clouds of radiation and leptons. The white dwarfs that once numbered in the hundreds of billions per galaxy have largely evaporated, their crystalline lattices dissolved by the patient action of quantum mechanics. The neutron stars have shed their mass through the same inexorable process, leaving behind only the photons and neutrinos that carry the memory of their existence. The universe's baryonic content, the ordinary matter that once seemed so fundamental, has been converted almost entirely into radiation, joining the photons of the cosmic microwave background in an ever-cooling thermal bath. The thermal bath continues its inexorable cooling across timescales that render even proton decay a recent memory. As the universe approaches 10 to the 100th power years, a number so vast that writing it in standard notation would require more zeros than atoms in the observable universe, the cosmos settles into its final configuration, a state of maximum entropy from which no further meaningful change can emerge. The black holes that once dominated the gravitational landscape have long since completed their evaporation. The largest supermassive black holes, those that once anchored galaxies containing hundreds of billions of stars, required the longest to surrender their mass to Hawking radiation. A black hole of 10 billion solar masses, the kind that powered the brightest quasars in the young universe, takes approximately 10 to the 98th years to evaporate completely. The final moments of these cosmic giants unfold in a burst of increasingly energetic radiation as their event horizons shrink to quantum scales, releasing their remaining mass energy in a flash that briefly illuminates the surrounding void before fading into the background. The universe that remains contains almost nothing recognizable from earlier epochs. The photons that once carried information about stars, galaxies, and cosmic structures have redshifted to wavelengths measured in light-years rather than meters. The cosmic microwave background, which at recombination had a temperature of approximately 3000 Kelvin, has cooled to values indistinguishable from absolute zero. Temperatures measured in fractions of 10 to the negative 30th Kelvin, so cold that the very concept of thermal energy loses practical meaning. The expansion of space has stretched distances to scales that defy comprehension. Regions that were once separated by millions of light-years now lie separated by distances measured in powers of 10 to the 100th light-years. The observable universe, which at the current epoch spans approximately 93 billion light-years, has expanded by factors that exceed the number of possible quantum states in any finite system. The concept of cosmic horizons, boundaries beyond which light cannot reach an observer, has become almost meaningless, as the universe has grown so vast and so empty that the probability of any two particles ever interacting again approaches zero. The particle content of this final universe consists almost entirely of photons, neutrinos, and electrons, along with their antiparticles where pair production has occurred. The photons vastly outnumber all other particles, their density having been augmented by the radiation from proton decay, black hole evaporation, and every other process that converted mass into electromagnetic energy. Yet even this photon gas has become so dilute that the average distance between individual photons exceeds the diameter of the current observable universe by factors beyond calculation. The electrons and positrons that remain represent the lightest stable charged particles, immune to the decay processes that dissolved protons and neutrons. These leptons drift through the void at velocities determined by the temperature of the cosmic thermal bath, velocities so low that their motion can barely be distinguished from absolute stillness. The neutrinos, even lighter and interacting only through the weak nuclear force, form an even more diffuse background. Their energy is redshifted to values that make detection impossible by any conceivable physical apparatus. Thermodynamic equilibrium has been achieved across all accessible regions of the cosmos. The second law of thermodynamics, which drove every process from stellar fusion to black hole formation, has reached its logical conclusion. Entropy, the measure of disorder and the unavailability of energy for useful work, has attained its maximum possible value for the given energy content of the universe. No temperature gradients remain to drive heat flow. No concentration differences exist to enable chemical reactions. No gravitational potential wells persist to allow matter to fall and release energy. This state represents what physicists call heat death, though the term carries misleading connotations of warmth. The universe has not died from excessive heat, but from the complete dispersal of all usable energy into the most disordered possible configuration. Every process that could extract work from energy differences has run to completion. The cosmos has achieved a state of perfect, eternal equilibrium from which no spontaneous change can emerge through classical physics. The arrow of time, which throughout cosmic history pointed from lower entropy states toward higher entropy states, has effectively ceased to function as a meaningful concept. With entropy maximized, there is no thermodynamic distinction between past and future. The universe has entered a state of temporal symmetry, where the equations of physics no longer preferentially select one direction of time over another. Events, to the extent they occur at all, happen with equal probability in either temporal direction. Yet quantum mechanics introduces subtle possibilities even in this apparently final state. The uncertainty principle ensures that perfect equilibrium can never be absolutely achieved at the quantum level. Virtual particle pairs continue to flicker in and out of existence throughout the vacuum, borrowing energy from the quantum fields for durations permitted by Heisenberg's uncertainty relation. These fluctuations, while averaging to zero over any macroscopic measurement, represent the last vestiges of activity in an otherwise static cosmos. On timescales that dwarf even the age of heat death, timescales measured in powers of 10 to the power of 10 to the 100th years, quantum fluctuations could theoretically produce macroscopic structures through pure chance. The probability of a random fluctuation assembling a hydrogen atom from the ambient particles is vanishingly small, but not zero. The probability of fluctuating into existence a star, a galaxy, or even an entire observable universe approaches zero so closely that the distinction becomes philosophical rather than physical. Yet the mathematics of infinity suggests that given unlimited time, even the most improbable configurations must eventually occur. Some theoretical frameworks suggest that the vacuum itself may not represent the true ground state of the universe. If the current vacuum is metastable, a local minimum rather than the absolute minimum of the cosmic energy landscape, then quantum tunneling could eventually trigger a transition to a lower energy state. Such a transition would propagate outward at the speed of light, fundamentally altering the laws of physics within the affected region. The probability of such tunneling events depends on parameters that remain uncertain, but the timescales involved would exceed even the evaporation time of the largest black holes by factors that challenge mathematical notation. The geometry of space-time in this final epoch depends on the precise value of the cosmological constant and the ultimate fate of dark energy. If dark energy remains constant, the universe continues expanding exponentially forever, with the scale factor doubling at regular intervals measured in tens of billions of years. This eternal expansion ensures that any particles still present become ever more isolated, their mutual recession velocities eventually exceeding the speed of light due to the expansion of space itself rather than motion through space. Alternative scenarios exist within the framework of theoretical physics. If dark energy increases in strength over time, a possibility called phantom energy, the expansion could accelerate without bound, eventually tearing apart all structures down to the subatomic level in a big rip, occurring at some finite future time. If dark energy decreases or reverses sign, the expansion could slow, stop, and reverse, leading to a big crunch that compresses all matter and energy back into a singularity. Current observations favor continued expansion, but the uncertainties in measuring dark energy's equation of state leave these alternatives within the realm of possibility. The information content of the universe in this final state presents profound questions at the intersection of physics and philosophy. The holographic principle suggests that the maximum information content of any region is proportional to its surface area rather than its volume, measured in Planck units. As the universe expands, its information capacity grows. Yet the actual information content, encoded in the positions, momenta, and quantum states of the remaining particles, becomes ever more dilute. The ratio of actual to possible information approaches zero, leaving a cosmos that is almost entirely empty of meaningful structure. The photons that carry the final record of cosmic history continue their eternal journey through expanding space. Each photon's wavelength stretches in proportion to the scale factor, its energy diminishing towards zero without ever quite reaching it. These photons encode, in principle, information about every process that created them. The nuclear reactions in stellar cores, the matter falling into black holes, the decay of protons in ancient white dwarfs. Yet this information becomes increasingly inaccessible as the photons redshift beyond any conceivable detection threshold, their message preserved but unreadable. The universe settles into its final whisper, a state of maximum entropy and minimum activity that nonetheless persists forever. the laws of physics continue to operate, governing the behavior of the few remaining particles and the quantum fluctuations of the vacuum. Time continues to pass, though its passage produces no observable change in the macroscopic state of the cosmos. The story of the universe, which began in the unimaginable density and temperature of the Planck epoch, concludes not with a dramatic finale, but with an eternal, peaceful stillness, a cosmos that has completed its thermodynamic journey and rests at last in perfect equilibrium.